academic meeting also an occasion to celebrate the 60th anniversary of Professor Sudeshna Sinha, who was a former colleague at the Institute and also one of the leading figures in the nonlinear dynamics community in India. I know Sudeshna probably doesn't like all this, but okay. So what I would do is, we have scheduled the first talk to begin at 10, but what I will do is give the floor over to the first session chair, Professor Rana Balakrishnan, also a former colleague, who would be chairing the first two talks, but because unfortunately she won't be able to present during the dinner, during which some of those reminiscences might be more of a more personal nature can be exchanged, I just give the floor over to her so that she can say a few words about her interactions with Sudeshna and so on, and then she can introduce the first speaker.
Excuse me. Okay, good morning, everyone. So happy to be here for the discussion meeting, and of course also to celebrate Sudeshna's 60th birthday. I know her birthday is 8th of June, and 7th of June, and we did correspond at that time. But I do want to say a few things about Sudeshna since I will not be here in the evening. First, when did I first meet Sudeshna? Way back in the late 80s, sometime when in Calcutta there was a conference on chaos and nonlinear dynamics, and it was organized by Meher Engineer, and Ram was also there, and Nilima was there, and Sudeshna, the young student of Ram, was there, very quiet. Yeah, of course, even though, of course, she's much younger now. Can't believe she's 60, okay? And she and I think she was always, she didn't interact too much. She was always there with some books. She sat with other graduate students because, she was getting, and I remember Ram saying that she's almost finishing Hamiltonian chaos at that point in time, correct? Hamiltonian chaos and trying to find periodic orbits, am I correct? Numerically? Okay. So then, and then of course we've been meeting off and on, and then she was in Trieste. And I was very happy that subsequently Sudeshna was able to join IMSC in the early 90s. And of course, both Kapil and Sudeshna, I was asking Sudeshna if Kapil has not come, he's busy, and Shruti, of course, and see all of them together, and Shruti was always in Sudeshna's office, and it was very nice, and although we did not collaborate because Sudeshna is mostly computational and chaos, and I am a non-numerical person doing solitrons, which is two opposite ends of the spectrum. But I also dabbled a little in chaos, an analytical thing, but I just gave up after that. But we did discuss off and on about some things. And now I just cannot believe Sudeshna is 60. And, what else I'm trying to recall. I think I have to give the floor to the others too. Okay. So happy birthday again, Sudeshna. And it's very nice that this discussion meeting is being held here in IMSC. And all our IMSC friends will also be here later. Thank you, Sitabra.
Ram, I understand that you won't be able to unfortunately stay for the dinner. So if you would like to take this opportunity to say a few words about Sudeshna before you start your talk. So Professor Ram Ramaswamy is in fact, as you guessed from Professor Radha Balakrishnan's words, the PhD advisor of Professor Sudeshna.
I'm ready for the roast.
No, see,
in order to roast you properly, Sudeshna, one needs sort of a spiritual accompaniment. So I'm not going to roast you. I'm not also going to, I mean, I didn't realize that you've taken us for a ride. For 6 months, she's been pretending that she's 60. Okay. Anyway, just to add a note of congratulations on having made it to 60 and not disappointed us, as you were pointing out earlier. No, it's just nice to mark the occasion. I think I'll just go straight into my talk at some point, if you don't mind. Also because my throat, my apologies, my throat is really awful. Managed to get a sort of pretty bad cold. Yeah. So go ahead, Radha.
Is there a timer? Okay, good morning, everyone, and welcome to this discussion meeting on patterns, dynamics in computation. And the first talk is going to be by Professor Ramaswamy, now from IIT Delhi, but of course we all know him from JNU, and he needs no introduction. So anyway, it's all very informal discussion meeting. So please, Ram. And the title of the talk is going to be?
I've changed it.
Oh, you have changed. Control strategies in dynamical systems. Okay.
Yeah.
You have half an hour, right? I mean, there's no...
Yeah.
Okay, fine. I'll tell you at 10 minutes.
Not to worry. No, thanks for reminding me, Radha. Sort of, I'm in my present avatar now at IIT Delhi, but for the longest time I used to be at JNU. And earlier, when Sudeshna joined me for her PhD, I was at TIFR. So I've been wandering. Okay, what I thought I'd like to tell you about is, the title is out there, Control Strategies. Okay, in the area of chaotic dynamics, in the area of nonlinear science, control has been a very common theme. And the idea that a chaotic system is unpredictable and subject to sensitivity to initial conditions made it almost an imperative that one learns how to control such systems. Now, control theory is an old subject, and one of the sort of, if you go to Wikipedia, at least to get a definition, the objective of control theory is to develop a model or algorithm governing the application of system inputs to drive the system to a desired state. So you have a dynamical system. It may have a multiplicity of possible states, and then you want to have a specific solution, this so-called desired state. And you'd like to do it efficiently. You'd like to ensure that there is stability. You'd like to do it fast. You don't want errors, and so on and so forth. Okay, so typical applications of control theory is by engineers to any kinds of systems. You would like a you'd like a plane to be flying in a regular trajectory. You don't want too much, you don't want it to be subject to too many fluctuations, and so on and so forth. Okay. So in 1990, the area of chaos control was, in a sense, officially born with the appearance of a paper called Controlling Chaos. And this was by Ott, Grebogi, and York, and it appeared in Physical Review Letters. And their idea was the following. They actually wanted to do away with chaos. So they said that, look, in any chaotic attractor, any chaotic system, you have a very large number of periodic orbits. So what we'd like to do is to control the system so that it does not show chaos, and instead we'd like to adjust the parameters somehow from time to time in order to stabilize otherwise unstable periodic orbits. Okay, so in general, for any chaotic attractor, the chaotic motion hangs on a skeleton of periodic orbits. The pity is that all the periodic orbits are unstable. So the Ott-Grebogi-York paper basically said, how do we make these unstable periodic orbits stable? All right? Okay. Also in 1990 was a paper that Sudeshna and I wrote along with J. Subbarao, who was a colleague at JNU and is known to, and the classmate of Radha and Bala. Right. And the idea, the title of this paper was Adaptive Control in Nonlinear Dynamics. It's been a sort of reasonably well recognized paper, fair number of citations, etc., the usual metrics, but it appeared the same year as Ott, Grebogi, and York. That paper, of course, has been vastly influential in, for all the right reasons. And nevertheless, already in 1990, we were thinking about the idea of control. Since this formed a fairly large part of Sudeshna's thesis, I thought it would be appropriate to not only talk about it today, but also to talk about it in slightly new language. So the objective of this adaptive control method was different from Ott, Grebogi, and York. The problem that our work was based on an idea by Huberman and Loomer, and the main thing was that supposing you have a system, a nonlinear system, operating at a specific state. Okay, it was operating in a way such that a certain dynamical state was achieved, and there was a perturbation. Perturbation where all the system parameters were changed or what have you. How could you engineer the system so that you go back to the desired state? So it's sort of typified by this. Supposing you were at a steady state and you went into some kind of, the parameters changed dramatically, how would you bring it back to the same steady state? And what you need is for the system to do it autonomously. You don't want to, you would like to ensure that irregardless of what the actual dynamics is, the state that is achieved would be the right one. And what we showed was that this adaptive control could work with fixed points, with periodic orbits, and all sorts of things. And later, so this was, there are many such examples and many studies that we presented in this paper in Physica in 1990. But then we went on to also, in later work with Nilima, to show how you could adaptively control to a desired chaotic state, not just a desired periodic state or a stable state, right? Okay. Okay. Now, roughly around the same time, another idea became very common in the study of nonlinear dynamics, and that is the idea of synchrony. The idea of synchronization, and there's been sort of scores of papers in this area. Yeah?
Can Bala ask a question?
Sure, of course. I had no idea. I wasn't aware of whether it was this.
You asked me the chair.
One never knows whether you're in the role of chair or in the role of...
That's very true.
No, sorry, my question interrupting flow. Is trying to balance a stick part of the Ott strategy, or is it adaptive control? What would you call it?
Okay, the example that it's part of the Ott strategy.
Okay. I see.
That's called a complete submethod.
Yeah.
Yeah, that's the one.
Yeah.
See, under normal circumstances, this would just fall over. Whereas what Ott, Gribaudy, and York did was to show that you could do whatever, etc.
Yeah.
All right.
So it's an unstable equilibrium point, but you're changing parameters in order to bring your hand.
Yeah, the oscillation of the unstable equilibrium point would in fact stabilize that point, and that would be part of that's the basic idea behind the Ott strategy. All right, but of course, I mean, to be fair, if the system was in a chaotic state, what Ott says, or what OGY say is that, look, we are not interested in that chaotic state. We would like to just go for the periodic orbit which is there. What we did, and I mean the paper with Nilima actually describes it in more detail, is that we were able to achieve a certain desired chaotic state. You may want that.
I should also mention that as it happened, the OGY paper became so big because Bill and all did that experiment which was supposed to be there. So I drilled them on the experiment. What they had done was actually closer to this rather than OGY, because the main problem with OGY is to isolate where the unstable point is in a real system. And they had not done it, and in fact they were just using parametric control as it happened, but they cast it in OGY language, so it became.
OGY is very difficult to do experiments.
Very difficult to do. So that's why
map-based
those guys hadn't actually done it. So I always thought, without realizing it, they'd actually done this rather than that. But that's a long.
Because we tried OGY experimentally, it was impossible. So we went to the map-based algorithm by Peng and Showalter, and there you can locate on the 45-degree line the intersection, the unstable period.
No, but
OGY is completely out of the domain of an proper experiment.
No,
maybe electronic.
My point of bringing it up is that in the year 1993, ideas came together. Right?
It's a citation classic of sorts, right? Garrel has put OGY's paper as one of the
5,000.
Yeah, of the paper. Sorry.
You remember Higgs? Okay. All right, so synchronization is another of the common themes that was going on in nonlinear science. And the basic idea is that, that you've got two oscillators of some kind, and as they interact, they adjust their rhythm so that they become identical, or I mean they become highly correlated, and in fact they could even become identical. Right. Now this idea started in the 1980s and culminated in another paper which is very well known in 1990, although the original idea comes from paper by Fujisaka and Yamada, and also to some extent the Afraimovich.
Was this 1990 the Pecora Carol? I
Yeah.
think later.
No, 1990 is Pecora Carol. Yeah, because I mean, following 1990, everyone was doing control. All right. I'm not sure, but I think we were unaware of OGY when we did our work.
Because we did it in the 89 of,
Yeah.
so we had actually submitted the paper before that paper came.
Yeah,
So I
yeah.
do remember.
All right. Anyway.
Yeah.
Okay. So the thing that Pecora and Carroll did, and they again have garnered a fair number of citations, was to show that chaotic systems could be made to synchronize via the so-called master-slave coupling, where one system drives the other similar system. So you have, let's say the Lorentz system and the Lorentz prime system. This is the master, and it essentially feeds the signal from the master into the slave. And in a sense, it's obvious that the master controls the slave, making this equation actually redundant. Now, it was presented in a way where we sort of understood it, as a process of synchronization. But one can also see that this is a control strategy. Because if you've got the Rossler master and you've got the Rossler slave, I mean, this is the Lorentz 1 and Lorentz prime, these two. If I now add these so-called controlling terms, essentially you get the slave. So you can think of the Pecora-Carroll algorithm of feeding one signal into the other as essentially a control strategy. Right? This is not often showed like so, but you will see why I'm sort of presenting it like this. All right. Now, again, just for the few who may not have seen something like this, this is a case where I switched on the master signal going into the slave at some time 10, just to show that prior to this master driving the slave, you have systems that are completely uncorrelated. And as soon as the master starts driving the slave, the two signals overlap exactly and they are identical.
They continue to be chaotic.
They continue to be chaotic. All right? So basically, up till time 10, it's this dynamics. After time 10, it is this dynamics. So it's a control strategy. So without being too subtle about it, I'm just saying that all synchronization is control of some kind. Okay, so I mean, this is basically to show that the dynamics becomes identical, the distance just goes to 0, all right? Okay, so chaotic synchronization is this phenomenon that I've just shown you, and it's been an important area of study in nonlinear science. The nature of the coupling, what do you have to do in order to make systems synchronize, what type of synchronization do you have, etc., has been very important. Lots of different kinds of coupling have been studied. There's a close analogy between the transition to synchronization, especially in ensembles of systems and phase transitions. So there's a lot of stuff. Okay. As I said, there's a virtual zoology of dynamics that can be classified as synchronization of some kind. All right? Phase synchrony, lag synchrony, stochastic synchrony, etc. Okay. So phase synchrony, for example, is when two oscillators will show very similar or have an identical phase without having identical amplitudes. Okay, so this is observed in something like the Rossler system. The Rossler is a chaotic attractor, and if you couple two Rosslers, you find that their amplitudes, which are plotted over here, become uncorrelated, although the phases are identical. Okay, so, right. Now, the point of this illustration is, of these kinds of synchronization, is just to say that if you take the variables of one system and you plot them versus the variables of the other system, if they're totally uncorrelated, you get a mess. If they are completely identical, you get a straight line over here. And if there is this phase synchrony, you get pretty picture. In short, as soon as you have any kind of synchronization, of what we call synchronization, you go from the whole space, the whole phase space, to a submanifold. Right? This is a sort of perfect synchronization, and this is called the synchronization manifold. All right? So, all these forms of synchronization in some kind or the other can be classified as generalized synchronization, which I will, basically, this is just to show you what complete synchronization is like, and this is what phase synchronization is like. But, all right. So, in order to give this the overall sort of framework, consider two uncoupled dynamical systems. So you've got the X system in as many dimensions as you want, the Y system obeying its own dynamics. Right? These need not be the same. You know, I've shown you Lorenz and Lorenz or Rössler and Rössler. They don't have to be the same. Couple them like so. So you have a coupling function zeta x, zeta y. That's in general a function of both these variables.
So now you have rendered the coupling bidirectional. Because before you were talking about unidirectional.
I'm going to be very general.
No, but when you were talking about control, it was unidirectional.
In
Master,
control, you would,
slave,
yeah, master and slave, you
unidirectional.
want it to be unidirectional. Right? Okay. So generalized synchronization is the condition that for some appropriate coupling, whatever that is, the variables of the two systems have a functional dependence. So the y variables, you know, if I couple them strongly enough or appropriately enough, the y's are unique functionals of the x's. All right? And this is this doesn't happen for nothing, because obviously if this is not here at all, that's absurd. And for specific zeta x and zeta y, you will find this function. This function can be differentiable, it can be non-differentiable, it could be all sorts of things. Right?
Do you have control over the function phi?
No, I'm going to, that's the point of this talk actually. All right. See, typically when you study dynamical systems, you say that, okay, you've got one system here, another one over here. I couple them like so. I think this is a reasonable coupling, and then out comes my phi.
Isn't it, there must be some kind of, to go back, under fairly reasonable general assumptions about the two zeta from two sides or zeta.
Yeah.
There must be some conduction mapping theorem or something which says the solution like this exists. You should be able to eliminate on the very general.
Okay, the difficulty, Bala, is that because these systems can be actually quite complicated, this phi may not even be a differentiable function.
Yeah, exactly.
It won't be.
Both need not be F. One can be G in the other one be F, right?
Which one?
The second thing need not be the same F, correct?
No. This is fx and fy. These are all different.
Different.
Yeah. In fact, the most interesting cases are when they're all distinct. All right.
And there's no limitation on the dimensionality of x and y?
No, they don't have to be the same. Although the example I will show you, at least they are, there's some similarity. But anyway, so the point is just this. Okay, ultimately I say that the resulting dynamics when you couple them in the following way gives you a lower dimensional submanifold. All right. And this is the so-called synchronization manifold. Okay. Now, in the so-called master-slave scenario, what you had is that here is the master, here is the slave. Right? So the master is unaffected by the slave. Okay, so this is just called the skew product structure. All right, and people have studied this for the last 20, 30 years. There's this generalized synchronization, etc., etc. Now, in response to your question, we started a few years ago asking the question, can you design the coupling so that you get a specific phi of x? Right? So that y becomes a desired function of x. All right. Okay, for this we just make a few assertions. The synchronization manifold is an invariant subspace. Once you come onto the synchronization manifold, you don't leave it. Okay. This is a lower dimensional subspace. And if the synchronization is stable, this manifold is transversally stable. Right? And perturbations away from the manifold will die out exponentially fast. Okay, so you're constructing a submanifold which has very specific dynamical properties. Okay, so as I said, the map need not be smooth. In the most interesting cases, it's not even differentiable, right? And I haven't been able to work with non-differentiable functions, but I'll show you a few things. Okay, so this is what we call the active viewpoint. It's a reverse engineering the process of generalized synchronization so that you tell me the function, I'll tell you the coupling. Okay. Now, this functional relationship, okay, I'm sorry, but this has just been awful to do notation in this system. But, so I've got the X system and the Y system. These are small x and small y, n-dimensional, m-dimensional, right? So now I've made one sort of capital X, which is just the x's and the y's all together. And I take this functional relationship and I put them as a set of constraints. These are the required, the submanifold is defined in the following way. So phi of x is equal to 0 is my submanifold, right? Okay. And in order to do this, the idea is actually a very simple one. I've got this submanifold in my phase space. The dynamics is going all over the phase space, so I want to add coupling terms such that the dynamics will come onto that. Okay, so if I'm roaming around over here, I come down to this point, and then I'm staying on the submanifold. If I have to stay on the submanifold, then my dynamics has to be orthogonal to the normals. Okay, so since that's what is said all over here, this is like constraint theory, that you bring the system to the submanifold where you want, and you can add any number of terms that will constrain it to that particular surface, and the motion stays on that surface. Okay, so that's the, all right. Now, little mathematics. So we want, y is equal to phi of x is written now in this particular form. We want it to be invariant so that a trajectory that is in m phi remains in m phi. Okay. The normals are at any point are just given by the first derivatives, and then do something. You want to add the specific coupling such that the original flow plus the coupling is always orthogonal to the normals, and that gives you the following equation. It's overdetermined. So you get, see, these are not all square matrices. While this coupling is guaranteed to bring the trajectory onto the manifold that contains a flow, the coupling is only defined up to additional constants, so long as this additional constant vanishes on the manifold. All right? Okay, so more or less this is the strategy. You define your submanifold and let it be smooth so that your derivatives, etc., are all nice. Once you've done that, you bring your dynamics by the coupling, you bring it onto that submanifold, and you keep it on that by requiring this condition, and you can define it up to a constant. So you can, for those who work in the area of chaos, you can make it Lyapunov stable.
Transversal line.
Right. Okay. All right. So the Lyapunov stability is really guaranteed by asking for. Yeah, sorry.
Can you go to the previous slide? What is capital NX?
Which one?
Capital NX on the RHS.
This one?
Yeah.
These are the normals, the vector of normals.
So what is the, I thought the LHS had the normal.
See,
Okay.
right?
Yeah.
And this, I told you this, so it was, I've done a bad job on notation, but it was really difficult. Okay, so, and this frac n is really all these,
And for so many notations.
what to do. Okay. So to get stability, you really need this to happen, and you want them to be all negative all over the place. You can get all this to be done, right? And yes, Sudeshna, this is related to adaptive control. I'll come to it later. So let me show you how we sort of work with it. The constraint submanifold is a parabolic surface. Right, I want x1 to be y1, x2 to be y2, but x3 squared to be y3. All right. So in this whole, see, this is a three-dimensional, so it's 6 dimensions. Now in the 6 dimensions, I put 3 constraints. 3 constraints means I'm on a 3-dimensional submanifold. This submanifold is curved. I mean, I can do it with a whole lot of examples. I'm just saying, this is curved, so it's there. All right. Put it through.
You need to ensure that the constraints are holonomic, right?
No.
Otherwise, velocity, then there'll be a problem, right?
No. We have time-dependent constraints also. Taken into it. Anyway, so that's the original system. Okay, just a little notation over here. The coupling functions are these. So when you see a vector of zeros, this means that there is no coupling on the first system. So it's master-slave. This is the master because, okay, so you've got these 2 systems over here. The coupling is added here and added over here. So if I now have the following situation, there's no coupling. I mean, the coupling term is 0, so there's no change to that system. And this is the coupling term that you add on this side. And the resulting dynamics is in green. So you see that the original Lorentz attractor is shown over here, and you find that this other one is, x3 squared is equal to y3. So it just becomes expanded. And you can see quite clearly how the curved manifold comes about. You can do this in many different ways. You can do it to make it a slave master. I mean, this is the slave, that's the master. You can make it bidirectional. And you just see that you explore different parts of this invariant submanifold. Okay, so all these forms of coupling will give you the same, it will give you constraint dynamics on this curved subspace, where the z variable of one is the square of the z variable of the other.
Sir, so in the original generalized form of the master slave.
So in the generalized form of the master slave equation, you had a parameter epsilon. So why is the epsilon in this implemented?
This, our formulation doesn't have epsilons in it. I mean, you can throw one in if you like.
Okay, so so these parameters beta and all these stuffs, how do you choose that?
Oh, this is the standard parameters of the Lorentz system. See the Lorentz. This is some 8 by 3, and this is some 28 or something like that, and that's 10. Those are the usual Lorentz parameters.
Yes.
Right?
Thanks.
Okay. Okay. So I mean, I can give you more and more examples of how to do this, but the point is that this is a constructive methodology. You design your coupling function in order to get the one submanifold that you want. Actually, you can do a little better. You can go on to spatial degrees of freedom. And in honor of Giorgio Parisi and the complexity Nobel, so to speak, right? I just want to appeal to the following fact that if there is, let's say, 1 million birds over there, the phase space that is being explored is not of dimension 3 million. Right? Just, because there has got to be separations, there are constraints of various kinds. I mean, it's not a 3-dimensional object, but it's also not a 3 million dimensional object. Right? So for example, you can take two such systems and say that if I pretend that these are spatial coordinates x and y for one system and for the other, I can make the separation between these a fixed number, a and b, right? Put it through the methodology, and you come up with these functions. This is the master, this is the slave, and I can add additional terms for stabilization, which, you see, note that the stabilizing function vanishes on the submanifold. So that's one system, that's another system, right? And one can do this to take arbitrary motion in 3 dimensions and make a whole flock of these move around together. Right? So the point is that this is completely controlled, right? Because you put them on a desired submanifold. Okay. So just to wind up, like the synchronization manifold, there is a submanifold that is relevant in the case of control as well. Right? And you can see control as a constraint that you're adding onto a system. With the coupling terms are, like forces that are forcing the system to your desired dynamics. This is just an analogy because we are looking at non-Hamiltonian systems. Right? The solutions that you get for any control or for any synchronization is not unique. Because once you reach the manifold that you want, you can add all sorts of terms that don't change the dynamics. Everything that will vanish, this is the usual thing, right? If it's a perfect differential, you can always add extra terms. But there are implications for stability, efficiency. There may be optimal couplings. Right? The control manifold may or may not be globally attracting. One has to worry a little about this. And you can always design this proper coupling for any, I should be more modest than almost. Okay, we've been able to do it for a few examples, and in which we were, being successful. For highly constrained systems, you may not even have the original dynamics. That's a problem with this general thing. And the general problem actually does not have a unique solution because there are many forms of the coupling that can give the same final objective. I was reading this paper again after some 32 years, Sudeshna, and I believe that most of all these notions, etc., were there somewhere in in our 1990 paper. So that was a good place to start exploration of nonlinear dynamics, chaos, control, synchronization, etc. And so I've been working with some gifted undergraduates, interns. Shahrukh is at IIT Delhi, was at IIT Delhi, and Amrita is now at University of Waterloo, someplace, right? And let me thank you for your attention.
When you couple systems like this, what happens to the Lyapunov spectrum? You force it to be on a submanifold. What happens to the
You want all those Lyapunov exponents to be negative, the transverse Lyapunovs to be negative.
Right.
That's part of the condition.
Does it increase the positive Lyapunov exponent?
Yeah.
See, so the eigenvalues of the Jacobian, you want them all to be negative.
On the submanifold, I see. Okay. Because very naively I would expect, for instance, if you couple Rossler attractors together, there should be some band merging and so on going on.
See, depending
if
on
it's
how
with
you
this
couple,
bidirectional coupling, I wouldn't expect the shape of the attractor to remain as it is.
no, it won't. But that doesn't mean that, you see, it'll depend on what this function phi is.
So the attractors may have different.
No, Bala, mine is not that given this coupling, given two systems and some coupling. It's not that. I'm saying that given two systems, and if I want them to lie on a particular surface, then I choose my coupling so that all these are true. I mean, this is a design.
Okay. Okay.
More questions?
Yeah.
We might actually even have a similar, I think we might have the same question. Yeah, so I was wondering if the two systems, like you had two Lorentz or two, if they were completely dissimilar, because we've had some thing where, the dissimilar systems, we are managing to get them more regular actually. So I was wondering if you all tried, say, a Rossler and a Lorentz.
We've tried Rossler and Lorentz. We've tried.
And so there was anything specific in the nature of the coupling or in the ease or anything? Okay. So what was the curve like at the end? Did it? So you had a Rossler and a thing, and you want to get them to a generalized thing. So what was the the one on the manifold? What did it look like?
Sometimes it just wrecks the dynamics completely.
That is exactly what happens in our.
It actually comes out in the formalism also.
It's a mutual depth.
Yeah, so that is exactly, we only managed to get mutual depth when we did them together.
Yeah.
And we did his experiments also.
But I'll go even further, because we managed to do that experimentally. It's very fascinating, especially I'm very intrigued by the last part, the spatial domain, because it's kind of mimics swarming and stuff like that. But
in my other talk, I have drones.
okay, but the point is, since if you're an experiment, which you're not, it's hard to envisage how by reconstructing a attractor using delays of the Ruehl-Tarkens method, would you be able to even venture close to getting the function you want? If you have only one variable in the cell, chemistry, current coming out, and you can do reconstruction, you can even attempt OGY, humongously difficult, nonetheless not impossible. I mean, at least to my knowledge, I can't see.
See, in this particular case, we have no dynamics. I mean, I don't know what the dynamics are. I just told Amrita that, I've got a system which is flying along this particular pattern. Some arbitrary curve, right? Here is a whole bunch of constraint systems that are following the same.
Okay, that's my concern. How do I get these constraints from just one variable?
Or discuss that we can get. This one, the last one.
These arbitrary motion, they're predefined, or is it like the arbitrary motion that you mentioned, is it predefined? Like you...
Okay. See, okay, so the idea was, supposing in a flock of birds, I don't know if there is one master bird and everyone else is following it. I don't know how that master is going to move, but let me assume that it moves in some arbitrary curve.
Okay, okay.
Can I then constrain all the others so that they will follow that?
Okay, okay. So here there is nothing like dynamic coupling or.
I don't have a dynamics.
Oh, okay, okay.
But over here, I mean, one of these birds could be the master.
Okay.
Or maybe there are 4 of them or something, I don't know. But just the idea that once I've fixed a master, then I've got a whole bunch of slaves.
This is absolutely the last question.
Yeah, hello. So for a master-slave coupled equations, do you expect that the slave dynamics will always mimic the same dynamics as the master, or by control we can have any desired kind of dynamics, like for the slave system?
If you have master-slave dynamics, in general, the master is just an unaffected drive, so that the slave dynamics will have some component of the master dynamics plus maybe something else.
Okay. So it's not always like that it will mimic the same dynamics as.
But it will have components of the same.
Okay. Yeah.
Think of a post oscillator.
Entrainment.
Big one?
Entrainment.
Well, I have just one question, but I'll ask you later because we're running out of time. Okay, thanks, Ram, for a very, very nice talk. The next speaker is Professor K. Murli from Anna University. Known Murli for a long time. Okay, the title of the talk is Harnessing Dynamical Patterns.
இல்லை இப்போ உங்களுக்கு இருந்துச்சுன்னா போடுங்க. ஸோ உங்களுக்கு வந்து விஜிஏ இருக்கா? அந்த பக்கம் USB அது. படம் கீனோட்டு தான். பிடிஎஃப் இருக்குது. ஓகே. இந்த பிடிஎஃப் நான் இல் கிவ் a try.
Mine is not working.
Okay. I'll on. Okay.
Give the HTML cable.
Okay. Okay. Sorry for the small glitch and other thing. Good morning to everybody. It's quite a privilege to be here and to talk about the kind of work which I am doing in collaboration with Sudeshana. To start with, so I have been blessed by many number of people. Okay, so I am always answerable to two persons in the world pertaining to the research which I am doing. One is my Professor Lakshmanan from Bharadas University. So another one is Professor Ram Ramasamy from JNU. So always whenever they meet me, they will immediately ask what you are doing now, what is your progress, what is your latest research, okay, what is new, they will ask. So I am always answerable, and that enthusiasm makes me to work so that I have to somehow convince them at one point. Okay. Right. So this is the title of the talk, and somebody a presenter. Okay, so you do one thing, just insert this one. Okay. So the talk is harnessing dynamical patterns, and I do hope many of the slides I have borrowed from Sudeshana's slides, and maybe the same slides maybe get repeated, and apologies for that one, because this is the kind of work which we are doing for the past 20 years or so. Okay. To start with, I wish to recall the words of Leo Katanov. It's an experience like no other experience I can describe. The best thing that can happen to a scientist, realizing that something that happened in his or her mind exactly corresponds to something that happens in nature. It's a great shock, and it's a great joy. It's a great joy with work with Professor Sudeshana, okay, for the past 20 years or so. And this topic, so we have many collaborators, okay, especially the Sudeshana is the driving force among all these contributions. Okay, and so first I want to recall my encounter, first encounter with Sudeshana. So I migrated from Trichy to Chennai in 1998. I joined in Anna University, and at the time I had very limited computational facilities. So I asked Professor Sudeshana, and she has recommended me to utilize the IMSc computational facilities in 1998 to start with, where she was sitting at the old building, was at the left-hand side of that room, and she enthusiastically recommended me. So then couple of years I just come here and do some computational work, and I go, something like that. And I think fondly in the year 2002, might be September or November, I really intrigued by this paper. Okay, dynamics-based computation by Sudeshna and Ditto, and I asked her what is the thing there. Can you please explain? And she was very passionate, and she was meticulously explained this stuff to me. And so then I tried to figure it out what is going on in this particular thing, and it's basically a logistic map based thing. What is that thing? And she explained. But suddenly she asked me, Murli, can you able to do some experiments with this particular topic, especially the thresholding based control of chaos? And then I blinked at that time, and I had no direct answer to that thing, and I told her that, okay, I will look into that. But apparently what happened is that in couple of days I have realized a kind of circuitry, okay, based upon the logistic map. And then I found that the kind of control mechanism which she was explained to me is nothing but a standard electronic clipper circuit. Then I tried to make use of that thing, and then things worked properly. And I think couple of days I came to her and discussed about her. Yeah, indeed I got that results and everything. Then she gave me some kind of parameters, and you counter check all these things. Then I immediately went back to my laboratory, and then I did the thing, but it works. Okay, but in a different scale. Okay, so whatever she done with numerics, I have able to replicate it in experiments in terms of volts. Okay, then immediately she came to Anna University and looked at that entire setup and everything, covering the entire table and in a student's lab, and she was very intrigued, and she wants to vary all the parameters of the system and other thing, and she was convinced, okay, things are working properly. Okay, so that's what the journey we have started, I think in 2002. Subsequently, in 2003, we submitted the work to Physical Review E, and a couple of papers in a same issue appeared. Okay, I do hope that is the 20 years of sustained collaborative effort which we had, and it's all started with this paper. But still we are sticking to this paper, and still we are exploring with different versions of the idea. Okay, so that's the point, and thank you very much for your sustained enthusiasm and collaborative support and other thing. Okay, right. So I hope everybody has familiar with this bifurcation diagram of this simple logistic map, and what we are interested is that we are simply going to take one time series of this logistic map with that particular parameter R, and if I plot the time series xn versus iteration for two different initial conditions, so you can get different types of patterns. So different initial conditions are going to give you different types of patterns. Okay, now the problem is that what do you mean by the thresholding of chaos? Okay, so consider a general dynamical system and choose a state variable to be monitored, and then suppose if that variable is going to exceed a preset value x star, then that variable is going to be restricted. Okay, it's limited at that x star itself. Okay, so this is the kind of thing she explained to me, and for me I just visualized in terms of a graph. Okay, a kind of transfer characteristics. So it means it simply look like this. If you have a x variable and you are putting some kind of x star, then you are going to have some kind of restrictions at that point. It's basically a kind of clipper. Okay, suppose if we vary that x star okay, along that y scale, then obviously it is going to cover a larger values. And what point, suppose if x star is beyond x, that magnitude or that amplitude of your input x, then obviously you are not going to have any control over that. There is no clipping and other thing. Okay, so that circuit, so this kind of transfer characteristics can be easily be mimicked in electronics, and the essence of that thresholding is like that. You have a variable, it's going to have this one, you put a threshold at a particular point, and obviously it's simply try to clip at that point. Okay, whatever be the kind of variable has that value below that x star is not going to be affected at all. Okay, that's a thing. So then for the logistic map, suppose if I put that x star at the 0.75 something like that, you will get a kind of a flat portion, so it's properly restricted at that point. And then now you can able to have a kind of set of values of x star, so that you will get different types of controlled periods. They are all super stable orbits. Okay, you are having all sorts of the controlled orbits now you are having. And so if I try to plot a kind of bifurcation diagram versus x star versus this xn, if I vary the x star value, I will get all sorts of controlled patterns. So this is that experimental circuit, I think, which we have did in latter part of 2002, but it was appeared in 2003 in Physical Review E. And this is fairly simple. Okay, it involves two multipliers and then a couple of sample and hold circuits to have that kind of sampling, and then that sampling will be controlled by the time series of pulses. And this is the guy who is responsible for having that kind of clipping. It's a kind of threshold detector. It's basically constructed with an op-amp and a diode, and this V0 actually plays a role of your x star. Okay, so now that x star is in numerics is going to vary from 0 to 1. Now in experiment it is going to vary from 0 to 10 volts. That's it. Okay, that is the kind of scaling kind of thing. Okay, and then I can put this V0 at will. I can simply vary that one, okay, using a power supply. So then I will get all sorts of dynamics is going on. For example, like this. So if I put that V0 is equal to a very high value, for example 11 volts or something like that, I will get the chaotic waveforms. These are all the kind of waveforms. It's a sampled one, it's coming out. And suddenly if I put that V0 value, for example about 6 volts or something like that, so in terms of numerics it is going to be x star is equal to 0.6 or something like that, I got this kind of cycle. Okay, and also it's going to spit out these kind of controlled orbits for different values of this thresholding level. Okay, so this is going to have complete agreement with the theoretical analysis, and now you try to see that. So now here also I am getting all sorts of periodic limit cycles for different values of x star corresponding to V0 in terms of that 10 volts magnitude. Okay, so that's a kind of one-to-one correspondence. Yes, sir.
By clipping, can you avoid chaos completely?
Yeah, so by clipping, you can avoid chaos completely. And also, I think in the latter part, we are going to create chaos also. Okay, we are going to have some kind of design also. I will try to touch upon that point. But now at present, here we want to create a kind of lookup table kind of stuff where a set of x star value will give you a set of controlled periodic orbits. That's the thing. One-to-one correspondence we want to have. Okay, right. So this is the thing, and then it been extended to a continuous system also, not necessarily a logistic map or one-dimensional map. It can be extended to a continuous system also. For example, familiar Chua circuit model, it's being like this, and this part is that actual threshold controller. Okay, so here also depending upon that value E here, you will get all sorts of thing. If that E is very large value, then you will get a double scroll attractor. If you vary that E value from large value to a lower value, you will get all sorts of periodic motions until you end up with a fixed point also. Okay, so that's kind of, so it works both for your discrete dynamical system as well as for a continuous dynamical system. Not necessarily a three-dimensional system, it can be extended to higher order systems also. Even a hyperkinetic system or a delay systems, it works fine. Okay, so mainly it's a kind of design strategy, that's all. So what you are having a kind of working model and you try to impose a kind of control in a very prescribed standard way and see what happens, that's it. Okay, so that the idea is we are going to create a kind of one-to-one correspondence between your input control value to that of the performance of the system, that's it. Okay?
Ram was saying it's prescriptive, actually.
Yeah.
It's really prescriptive.
Yeah,
So
prescription.
If you want this, you set this.
That's it.
No calculation or calculation done
That's it.
beforehand.
Okay, right. So now this one, this is standard threshold controller can also be used as a kind of nonlinearity to start with. So then we can able to design chaotic circuits also with that threshold controller. Okay, so this is one kind of idea, and so it was done with Dr. Raja Mohammed, and this is basically a threshold controller. Okay, so that threshold controller actually plays a kind of nonlinearity there, and then if you have a proper dynamical system with a proper dimensions, indeed you can able to get this kind of attractor, and also the threshold value can be modulated. Not necessarily it has to have a fixed value, it can also be modulated in terms of a waveform, external waveform. Maybe it's a square wave or a kind of pulse. Okay, so you can create multi-scroll attractors also. So that threshold controller now plays two roles. Either it can control chaos or it can also create chaos.
But this is prescriptive, not predictive.
Yeah, it's prescriptive.
You cannot predict what
No.
you're going to get.
No, you have
No.
to do that beforehand and then you
Yes,
right.
that's it. Okay, right. So now the playback time for this stuff. Okay, so here in semiconductor industry and other thing, starting from 1960s, and Gordon Moore of Intel Corporation paraphrased that roughly between 16 months to 24 months, we are going to pack twice the number of transistors in a given square inch of the silicon area. Okay, I think at present we are at 4 nanometer technology. The same things more or less we are having about 8 billion transistors got packed into a 1 square inch silicon area. So automatically what will happen is that if you keep on increasing this the number of transistors and you are packing more number of transistors, obviously what happens is that you are reducing the size of the transistor, you are reducing the operating voltage of the transistor also, but at the same time what happens is that the transistor will act like a switches, so they obviously emit lot of thermal or heat generation. So it obviously it will try to increase the floor level noise. Okay, so now what happens is that for each technology you are reducing the operating voltage of the transistor, but at the same time you are increasing the floor level of the noise. Okay, so then actually we are not going to answer this one directly, but we are trying to get a kind of help from the nonlinear dynamics, whether we can have some kind of answer to this system. We are not actually solving this kind of problem now, but we are giving a kind of idea that the dynamics can have some kind of help to give some kind of alternatives. Okay, and then the idea is that is it possible for us to realize the kind of system which we are working now with the standard transistors available in the market. Okay, that's the thing. So now two answers. First one is that suppose if I have a kind of circuitry occupying a particular silicon area, so far engineers are designing the kind of silicon area is going to be a kind of circuit is static. It will perform only that particular function. But now you try to visualize in an alternative way. What will happen if the circuit occupying the same silicon area is going to have different functionalities? If that is the case, then obviously you are talking about you are implementing more Boolean functions, but still you are operating with a standard circuit occupying the same silicon area and could try to get the kind of same power and other thing. Okay, so that is one question we can answer. Another one is that how we are going to circumvent the problem of floor level noise increase. Okay, so these two kind of problem which we are having in mind, and so in due course we had some kind of design aspects and other things. So at one point we had a kind of idea that okay, there is a possibility that we can try to have an answer to these two questions. Okay, the practical questions, right? So for that thing we are first try to harness the chaos, and then we are going to harness the chaos to design a flexible hardware by exploiting the one-to-one correspondence between the threshold and the kind of controlled periodic orbits. And it turns out that we are going to create a kind of chaos-based logic gates design, and then that chaos provides a library of patterns depending upon the kind of control which you are using. And then the sensitivity initial condition provides a fast switching different patterns you are having, and then control mechanisms to select patterns at will and then switch between them flexibly. Okay, so these are all the kind of opportunities been given by this dynamical system. And programming threshold activated chaotic elements by fixing threshold values, so some input output relations operations are performed properly. And the idea is that by utilizing a single chaotic system, okay, we can implement different types of Boolean functions. So that's the kind of idea which we are having in mind. Okay, so for that what we are having is that we are trying to create a kind of dynamic architecture, okay, where we are going to have a kind of flexible implementation, and the initial condition is going to get altered in such a way that you are going to fix some initial value x0, but that one is going to be modified according to your two logical inputs I1 and I2. So now you try to visualize that this I1 and I2 are a kind of random square waves are going to fluctuate between some 0 value to some high value. So for example 0 volts to 1.2 volts or something like that, it is going to fluctuate. Once you are adding this I1 and I2 to random square waves, then you are creating a kind of 3-state pulse. Okay, 0 volts, 1.2 volts, then 2.4 volts. Okay, so depending upon that 0-1 combinations of I1 and I2. Okay, right. If so, then what happens is that now you try to create a kind of working model where that system accepts a set of inputs and you are getting a kind of output. Now you try to create a kind of a pattern. So for this set of inputs you are getting this set of outputs. Suppose if they are fall into this kind of satisfying this truth table, then obviously you are talking about you are implementing a logical element. That's it. Okay, so now you don't need to worry about the kind of what goes inside that black box. So that black box is your dynamical system. It accepts your input, it's spitting the outputs. If there exists a kind of one-to-one correspondence satisfying this truth table, then I am done. So obviously I am doing some kind of logical operations. Okay, so that's a basic idea. Then obviously it has to satisfy all these necessary and sufficient conditions. And then for this particular logistic map, for a same threshold value x star, now you try to see that for different initial values, I can migrate from AND gate to XNOR gate. It's covering all sorts of fundamental logical operations. Okay, so apparently what happens is that I am fixing my parameter of the system, so that R is equal to 4. Where the logistic map is exhibiting this chaotic behavior, and the threshold is fixed. Now I am having a kind of initial condition x0 acts like a kind of knob, so I am simply tuning that knob at will. Okay, so I can migrate from one logical operation to the same logical operations. Okay, so now the black box is same. Okay, so it's not static now, it's a dynamical one, and then I am just controlling that value x0. So the same guy is going to perform different types of Boolean logical operations. Okay, so I'm creating a kind of dynamical logic cell. Okay, And then in this dynamical logicals, we are having a kind of predetermined dynamical logical configuration. Outcome dependent dynamical logical configurations can also be done. And there is a possibility of the hardware design evolving during the computation itself. On the fly, I can able to change my initial value so that after that operation got performed, I can migrate to that next operations immediately. Okay? Right. 5 minutes, okay. So this is the kind of entire circuitry and other things. This is for one iterations we got this logical outputs and other things. So, okay, so on. And then we can extend this one for higher order iterations also. Okay. And then you try to see that a single logistic map itself can able to show all sorts of operations. It can, okay, depending upon that x0, and then you for different iterations also it's going to split. But the advantage here is that if you are going to operate with multi-input logical operation, there is a possibility that, okay, one iteration will give you some kind of output, some another iteration will give you some other output. Okay, so obviously with the same circuit, with the different iterations, you are going to get different types of logical operations. Okay, right. So now to want of time, I skip all these stuff. I finally show the answer to the second question which we have posed. Okay. Yeah, so this thing. Right. So this one is that kind of letter was. So here again you are having the standard Chua circuit based logic operations. Now what will happen is that what will happen if I try to introduce a noise to my control signal. Okay. So now due to the robustness of this kind of control, even under the presence of noise, the system emits the kind of intended output, but for only for a moderate noise. So now it has a kind of possibility that is it possible for us to tell what will happen if I have a kind of noise. Okay, for example, this is an electronic circuits working under the floor noise. What will happen? It's actual logical operations and other thing. Okay, so for that thing, so now let us say we came up with the kind of idea. It's an extension of that idea about we posted about 10 years back. And this work combines the ideas of chaos computing and logical stochastic resonance together. Okay, so in chaos computing model for generating logical output from the nonlinear map, we use a threshold detector. But now you try to visualize that a standard stochastic resonance system can act like a kind of threshold detector. Okay, and that stochastic resonance element will work only under the influence of an external moderate noise. Okay, so that will try to have the kind of idea that we can get a kind of reconfigurable and a noise assisted logic just by varying a single control parameter, for example that I0. Okay, so this is that standard model which we are having. This is that schematic which we are having. So now your inputs is going to be nonlinearly transformed. It's fixed by your logistic map, and that goes to your bistable system G of X. Okay, and that will give you this kind of response. So now you try to say this is the nonlinear transformed inputs goes to your bistable system, and for very low level of noise you are not getting any kind of meaningful logical output, and for larger amount of noise also you are not going to get any logical output, but only for moderate noise you will get this one. Okay, but now you try to see that one, the same guy what we have done for that chaos computing kind of stuff now works, okay, the same manner, but to get a proper logical output you need the presence of noise. A moderate amount of noise you need, that's what you are having. Now you can able to see that you are creating a kind of noise assisted reconfigurable logic gates. Okay, now the idea is that depending upon the kind of nonlinear transformation you are having, you can create more complex Boolean logical functions also. Okay, from a same system. So that is the kind of catch point here, and so this is the kind of proper noise strength and that initial value you get this kind of stabilized figure. And this is the proper experiments which corresponds to the kind of numerics which we have done, and this is an actual experimental results. Okay, so that summary is that nonlinear systems are abundant in exhibiting wide variety of patterns. Our central idea is to harness dynamical patterns and determinism for the design of computing devices. Okay, we have indicated the directions for using the interplay of noise and nonlinear dynamics to obtain reliable logical operations. Okay, and then finally the combination of research directions in chaos computing and logical stochastic resonance has potential to realize noise assisted reconfigurable logic gates. Again, I want to recall the quotes of John von Neumann. The sciences do not try to explain, but they mainly make models. Okay, the models are nothing but a kind of mathematical construct, and the justification of that mathematical construct is solely and precisely that is expected to work. Okay, so it means that we are having some kind of thing, a kind of payback time, where whatever be the kind of experience we had for the past 20 years or so, okay, now we have arrived with a kind of full circle in the sense that we are having a kind of model actually is working for some kind of useful applications. Okay, thank you.
Just one question.
Yeah.
You talk about this, I might have missed it, Murli, but this logical stochastic resonance, I didn't see a subthreshold signal. So is it a logical coherent resonance actually?
One minute.
Oh, it's a coherent.
That was the one which flashed past.
Okay, it's a coherent resonance, right? There is no subthreshold signals.
Yeah, subthreshold. This is subthreshold.
No, the other one,
Which one?
this, but you should be able to do it with noise as well, right?
Yeah.
So that's you have seen logical coherent resonance.
Yes.
Okay. Oh, I didn't know.
As a
Yeah.
Okay.
So actually I skipped that part for want of time.
Sorry.
Okay, right. Yes, sir.
I haven't thought about this adequately, but when you take this logistic map at r equal to 4,
Okay.
and then you clip it off, below 0.75 for x star, you should get a super stable orbit, right? I mean,
That's exactly
Yes,
what
sir.
happens. Up to, sir, because it always cuts the
cut at point, yeah.
by design.
So it becomes super
always.
stable.
It will be super stable. After that, it will not cut the plateau.
Correct.
So then you will go to 2, but
Yeah,
the
2 and so
sequence
on.
is very different.
So is there a sequence? I know it's not going to be anything as complicated as Sharkovsky, but is there a sequence here?
So actually, I'd written a law with the symbolic dynamics of that beheaded map, and every single cycle has a window.
Okay.
And every cycle may have more than one window. It's not a unique window also.
Okay.
And there are sequences, but they do not quite coincide with the
No, they
cycle
won't.
scale.
Yeah.
They won't, and they're
Because
not
you had
expected-
period 3 appearing right in the beginning.
Right, yeah. So it's a different sequence, but it's a well-defined
Well,
sequence.
okay, thank you.
I mean, you can do the symbolic dynamics, exactly.
So, and again, I want to make a kind of statement that Professor Balakrishnan was my MPhil dissertation examiner. Okay, so I was being examined by him in, I think, way back in 1987. Okay, in Bharadas University, and so that's a starting point.
So we have
Okay,
all the people.
yeah, because their encouragement are the thing, I am standing here now. Yeah. Thank you very much.
Thank you, Murli, for a very nice talk.
Thank you, Radha. So we will now break for coffee. So the coffee has been near the elevator. So I think Shakti can show the way. So please try to be back here on time. That's 11:30, so that we can start the second session, which will be chaired by Professor V. Balakrishnan.
can I just
Yeah, please.
You're going to be here till lunch? You're going to be here till lunch? Yeah. So you'll see what I'm... Boss, the experiment बहुत मुश्किल है. आपका वाला. I was thinking about it. I don't know how. Actually, that was... You'll be here, right?
So the chair for the current session is Professor V. Balakrishnan.
Thank you. Yeah. Maybe start? Maybe start? Are we waiting for the cameraman? Are we all set? Maybe start? Welcome to the session. There are going to be 3 talks here. The first is by Professor Nilima Gupte on climate network analysis of extreme events, tropical cyclones. Nilima.
Thank you, Bala. Let me start by wishing Sudeshna a happy birthday, very late, although I did wish her at the right time. Yes. And this is my second Sudeshna 60 conference, but it's a great pleasure to have something in person rather than over Zoom, although I must say that was fun enough. That was not at all bad. Yeah. So I actually wanted to talk about, Sudeshna and I have collaborated a lot over the years. So in fact, I was thinking that I would talk about not our first paper, which Ram already talked about, our first collaboration, although we did something on adaptive control and patterns.
Patterns.
So yeah, that would have fitted very nicely. Yeah.
Patterns.
Yeah.
But anti-control Ram already said.
Yeah. But then I thought I'd talk about our last collaboration, which is, except that I would have had to make the whole set of slides for it all over again. So next time, okay, your 65th birthday, Sudeshna, we'll do that. If I am still mobile by that time.
And you have lots of notice to make slides.
Yes, I have lots of notice to make slides. The other thing which I wanted to say was that we've collaborated a lot over many years. We have shared students, we have shared postdocs, and we have shared much gossip. Okay. So, I mean, I want to tell you a small story which I won't repeat in the evening because I already have many stories. But this is what my husband Rahul Basu, who worked in this institute, used to say. If Sudeshna came over, then in the evening he would say to me, so what is happening in math science? To which I would say, I work in IIT, not in math science. To which he would say, but Sudeshna came in to see you today. What did she tell you? I said, okay. So I would tell him, she told me this, she told me that, she told me this, she told me that. And then at the end of it, he would say, at least half of it I didn't know.
That would be of help, as they say.
So we have done a good job of spreading information over the years, and we'll continue to do so. So let me get to my talk. So this is work which we have done. This is work which we have been doing over the last 4 or 5 years, and it's quite intricate work. And plus, all the COVID, etc., has also been a factor. But I've had an excellent postdoc, Rupali Sonone, who did the bulk of this work. My student Ruby has also done a little bit of this work, but that's not what I'm going to talk about today. I should tell you why we got into tropical cyclones. We got into tropical cyclones simply because one day we were shutting down the systems because a cyclone was coming, and we said, we are working on climate phenomena. Anyway, this is passing over our heads. Let's see if we can say something about it. Okay. So, as I was pointing out to Bala, all the cyclones that I'm going to talk about have passed over our collective heads. So, I think you might recognize some of them. Okay. So, first thing is about networks. I think you all know about networks. So, this is just for the general audience. So it's a collection of nodes and links, and they have proved to be an important paradigm in the analysis of complex systems. And the way in which they have proved to be a paradigm in the analysis of complex systems is that it helps to organize very complicated information in a somewhat systematic way. And once you have taken your information and you have constructed your network about it, the analysis of the network can actually tell you something about the complex information that you are organizing. Okay. So they provide an important tool in the visualization and analysis of large data sets. And that's the way in which the field is going these days. If you have a huge data set and you don't know how to organize it, this is a good way to try. And these can also be used for the prediction and analysis of extreme events. We've done some work which talks about the analysis, the prediction and analysis of El Nino and La Nina events. Okay, and there they do a fair job, I should say. Here I will not be able to say anything about predictions because we have not got that far yet, but I'll tell you something about the analysis. Okay. Okay. So what are climate networks? So this is a very important class of systems where statistical correlations in huge data sets can be conveniently visualized. They can be efficiently analyzed and used for effective predictions of natural phenomena. And in the context of climate networks, how do we construct climate networks? We construct climate networks via the statistical correlations between data at different geographic locations. And here they provide information on what are known as teleconnections, which I will talk about by and by. Then the identification of teleconnections, this provides insights into climatic phenomena. And the examples where you can actually analyze this is pretty complex weather phenomena, like El Nino, La Nina, Indian monsoon, North Atlantic oscillation, etc. Okay. And here we use this in the case of tropical cyclones. One thing which I want to tell you is that when we first started working on this, something like 6 years ago, this was after Rupali just joined as a postdoc and I was scratching, I had given her something to do. But one day I came across a PhysRev-led paper and I realized that, look, I've always wanted to work on climate, okay? And this is thanks to one of my very senior colleagues, namely Professor V.S. Murthy. Okay, and he was interested in this kind of phenomena, and he used to organize these small meetings where, in fact, El Nino and La Nina were talked about. Okay, and I thought this is a nice thing to do. I also thought that this is the kind of problem which a huge place like IIT should be doing, instead of doing, you know, small things here and there. Okay. Except that climate is a very complex subject. Okay, people have, after all, been working on this for God knows how long, and there's a huge community which works on this, and they work on different aspects. Okay, so there is climate phenomena, which means there's phenomenology, which is so vast and complex that none of us can effectively get. For us to, each one of us can only get to know a small section of it. We cannot possibly get to know the whole thing. There are, after all, specialists who know the whole thing. Okay. There's also climate dynamics models, which in fact people use in practice. People use these in practice for weather predictions. People use these in practice for weather predictions, and there is a variety of models which work quite well. Okay, so for example, if you have lived in Europe, you know that at least 3 days in advance they know what the weather is going to be like. Should you put your snow tires on or not? That kind of thing. Okay. Similarly, it's true in America. But on the other hand, can anybody say anything about the Indian monsoon? No. We still don't have models which are actually sufficiently sophisticated to make any reliable prediction on any of these. Okay. So climate dynamics models are so complicated that in fact that's another large regime by itself. All right? That's another large regime by itself, and they are so complicated that it's hard to even call them theoretical models. I don't know what to call them actually. They are large, complex models which are, in fact, they depend on so many parameters, so many variables, so many things that really they are a world by themselves. All right? So Climate networks are a different matter altogether. See, climate networks are actually constructed on the basis of data. And I don't know if I mentioned this right now, but let me tell you right now. There's a huge amount of data which is available. When I first started working in this, I was quite startled at the amount of data which is available. There's data available at every latitude and longitude intersection. And there's all kinds of data. There's sea surface data, there's high in the air data, there's wind data, there's ocean current data, there's thermal data. You name it, they have been collecting it. Not only have they been collecting it, they have been collecting it for years. Like when we did the El Nino La Nina stuff, we analyzed 40 years of data, or rather to be exact, 39. This of course is a very small sample. Okay? So when I actually was looking at this, as I told you, I was actually looking at a journal, and what I found was a physical review letters which was done by Havlin's group. Okay, so a number of people, number of groups have been working on this kind of thing, and there are one or two groups which actually have been applying. We have been constructing climate networks and have been constructing, have been analyzing climate networks. So Havlin's group is a major one. Jürgen Kurz's group is another major one. And when I saw those papers, I saw that most of the ideas, firstly, they were constructing a network via correlations. Correlations are a physicist thing. So we can very well construct a network via correlations. And secondly, they were using a lot of percolation ideas. And then I thought, see, this is one thing which my advisor told me many, many years ago. When you want to do something that you don't know, start with something that you know. Okay. And I said, climate, it's a whole new world, but percolation I know something about. So let's see if we can do something. So that's how we started. And okay, so here is the data. I should tell you that the data is freely available. We got it off public websites. Okay, and there's a number of websites. This is the one what I've shown you over here. This ECMWF, European Center for Medium Range Weather Forecast. This is actually one of the sites. There are many others, okay, which in fact store the same data. All right, you will get these data sets everywhere. But they are examples of what are known as reanalyzed data. That means they take the data, they clean it up, the way in which each site cleans it up, and the details of how the cleanup is done, how the averaging is done, what is the rate, what is the sampling rate at which they store the data, all that can be different. All right, and on the other hand, if you are going to construct a network out of it, it doesn't matter much. So you don't really have to worry about it. Any of them will do. I'm trying to tell you people this because I see lots of students and postdocs at the back. And as I told you, I always thought IIT should do a problem which is commensurate with its size. And I think you people should do a problem which is commensurate with your age. And I think you are the right. So I'm going to use a very specific data, which is a data set for near surface air temperature. So near surface this is the pressure. You can have data higher up. Okay, so you can get data at other pressures. This is between 1979 and 2018. I think, no, we didn't do 2019. For n equal to 726 nodes, and that is latitude and longitudinal points at a grid resolution of 7.5 degrees. So this is the data as it was. We didn't use all of this and this resolution. We used we used a part of this data. So that's something I will come to again.
This is over land or sea? Or both?
It's near surface.
Yeah, near surface, but is it over land or sea?
Both. They actually record Yeah, you were asking.
I can see the point commensurate with the age.
I'll explain later at the end of it. These are modern problems. All right? So don't get into elderly problems. We are not. So what is a tropical cyclone? In principle, you all know, which is that a tropical cyclone is a large-scale air mass with inward spiraling winds rotating around the center of low atmospheric pressure that originates over the warm tropical ocean. Most of these start over the ocean, so kind of related to ballast pressure. And you probably already know this. And there is a process which leads to the development of a self-sustaining surface concentrated vortex. Okay. And the intensity of the vortex, this partly governs the flux of energy from the sea surface to the vortex. Okay. And this is enough to maintain and to amplify the vortex. So actually this is the reason why your cyclone gets stronger as it goes over the sea, and it essentially dissipates as it comes over land. You are all, I think, living here, so you know this, that after it crosses over to land, it is not such a fearsome object anymore. So a typical cyclone lasts up to 3 to 7 days. Okay, thank God. Although I'm going to show you an example of one where what they call the cyclone lasts longer for reasons which I really don't know. And I should say that various experimental factors such as sea surface temperature, relative humidity, vertical wind shear, relative vorticity, all kinds of things, many others, they influence cyclone genesis and development. So, more information. The Indian Ocean basin, so this is tropical cyclones, okay? So you will have heard of typhoons, hurricanes, and these here I'm which are all belong to the same class, all right? I'm going to talk about tropical cyclones, which are mostly in our vicinity. As I told you, this happened, I started looking at this because we were shutting down our systems. Okay? There were things passing over our heads. And the Indian Ocean basin, including the Bay of Bengal and the Arabian Sea, this experiences bimodal cyclone seasons, on an average 5 to 6 tropical cyclones per year, with a primary maximum in tropical cyclone frequency during the post-monsoon season. So now actually, okay, so watch it. We need to shut down the systems again. And a secondary maximum during the pre-monsoon season, all right, which is April, early June. Although you seldom see them here. This year we did. Okay. Such tropical cyclones, they can cause severe potential damage, you know that. They used to cause terrible damage. Nowadays, thanks to all the warning systems that we have, they don't anymore. Okay? And therefore, the analysis and prediction of tropical cyclones, it's an important theoretical and practical problem. Ask any fisherman. Okay. So how are you going to construct the network? Okay. So I'm going to tell you quickly how to construct the network. I don't really have much time left because I've spent a long time on the introduction, though I wanted to. And I'll just tell you how we construct the network, what are the quantities that we analyze, and what are our results. Okay. So I may take 5 minutes extra, Bala, please bear with me. So all this I already told you. And see, remember, we have data, we have it for every day for 39 years. Which part of the data are we going to use? Okay. So what we did was we chose a grid which is essentially over the Indian Ocean. Okay. And these are the longitude values and these are the latitude values. I should actually had a picture somewhere later on. I have a picture which roughly shows you which is the region that we are working on. Okay. And we constructed a network for each 15-day period with a 0 to 7 day time lag. What is the time lag I'm talking of? That's because we are calculating the correlation via the Pearson correlation coefficient, and that has a time lag, as you will see when I show you the formula. Okay. So it's remember, a cyclone only lasts for 3 to 7 days. Okay. So how much data are you going to take? So we took 15 days, and I more or less arbitrarily said 0 to 15, 1st to 15th of the month, and 16 to 30th or 31st of the month. Okay, so 15 and 16 days depending, and that worked quite well actually. So how do you construct the correlation function? We construct a cross correlation function that's over here. The Ty of d, this is average data. So basically what is Ty of d is the mean temperature on a day d, and from that you subtract out the mean T tilde of d, that is the T tilde over this mean is over the number of days that you are considering, or in fact, sorry, it is over that day for as much data as you have or want. Okay, so we did this for the 15 days, and and you divide it by the standard deviation. Why is this done? This is essentially done to smooth the data. Okay, and here again, if you do it with the raw data, it doesn't make much difference. All right, so that's something which we verified, and this is the cross correlation which we have defined, and the cross correlation that we have defined is actually over different spatial locations. The spatial locations are the different latitude and longitude points. Each pair of latitude and longitude points, they actually define the I and the j. Okay, and this is how you construct the cross correlation function. You can see this. So this is our standard cross correlation formula. This is the Pearson correlation coefficient formula. There's nothing special about it. This is the one which we construct the network out of, and what it does, you can see from what is in the formula itself. It looks at what is the correlation between either the scaled or the raw temperature at a given point on a given day, and one which is previous to that day. Okay. Tau for this network which we are looking at, this goes from 0 to 7 days. Okay, so we look over a 7-day correlation function. If you are looking at different climate phenomena, then you need to do something different. Okay, all right. The averages are actually taken over 15 days. All right, and these averages, that is the correlation averages, those averages are actually taken over all the years. That's 5 years, 2013 to 2018. And I already told you that tau is 0 to 7 days. All right. So this is how we construct. So now how do we construct the network? We add see, each one of those correlations, they define the strength of the link between I and j. And we start with the highest value of the correlation. We take the maximum. And we add the links one by one. That is, we first start with the highest weight, that is the maximum of the cross correlation function. And we continue selecting edges ordered by decreasing weights. Okay. So as we decrease, we start with the highest value of C and we keep coming down. Okay. So basically, as we keep coming down, the network grows. Okay. And there's a point at which the network connects completely, which if you have ever studied percolation problems, then that is the point at which you actually get a giant component in your network. Okay. So you might have seen this. So basically the order parameter of the system is the size of the largest cluster, which is the cluster being the collection of linked nodes.
You could have also easily have made a weighted network, right, of it?
I don't want to. Okay. I mean, in the sense, it's already weighted in an indirect sense.
That's what. So you could have had the adjacency matrix with just the weights.
Yeah. But see, it's a question of what are the weights here, the correlations. Okay. Right. I mean, that is the obvious one. Yeah. Here now, the more correlated it is, the fewer links there are, because you are going up, you are starting with it, and you are coming down.
Yeah.
Okay.
Yeah, I got your point.
You got the point. So this is the way in which, yeah. Okay. So we define the normalized cluster, which is the order parameter, and we define the susceptibility, which is the usual way. Okay. So we are now done with forming the network. We have defined the order parameter. I already told you these. So Now we changed the resolution. So the resolution is now about 0.75 degrees. That's about 83 kilometers. So our data is at intervals of 83 kilometers. And so this gives us 10,260 nodes which are scattered uniformly in the Indian Ocean. Okay. Networks are constructed for the months of October, November, and December 2016. There are 2 networks for each month. Okay, so there are 6 networks. Okay. This is for 2016. There were 3 cyclones in this period. This was a bad year. There was Cyclone Kyant, there was Cyclone Nada, and there was Cyclone Varda. Varda actually hit Chennai very badly. If you were in Chennai at that point, you would remember that cyclone because there was widespread trees falling, electric supply gone for 2-3 days. I was lucky I was not in Chennai in 8 days. Okay. So now I'm just going to show you the results because I think I'm out of time. So what do we see over here? So the first thing we see over here is Cyclone Kyant. Let me show you. It's the same cyclone. The sea resolution is slightly smaller, so therefore it shows you slightly more detail. And look at what it shows you. You look at the order parameter, that is the red line over there. And you look at the susceptibility, that is the blue curve over there. And you can actually see that this network shows you can see that there are discontinuous transitions here. Okay? So if you look at the order parameter, you can see that as for changes in C values, you see steep jumps in the order parameter. All right? Correspondingly, of course, you see large jumps in the susceptibility. Okay? So this is now the network, the left side network is constructed from 1st to 15th October 2016. The right side network is constructed from 16th to 31st October 2016. And what happened over here, Cyclone Kyant actually created havoc between 21 and 27 October. Okay. Kyant wasn't actually that bad. When I show you a table, you will see that the wind velocities weren't that large. All right, but if it wasn't for the other 2, we would have said it was bad enough. All right. So see what you see over here. If you look at Kyant on the left side, then see this is 21st to 27th October. So the first network which is constructed, the one which you see on the left, actually is pre-cyclone. All right, but in the pre-cyclone network, you already see a number of discontinuities and you see a large number of them. If you look at the second one, which is 16th to 31st October, then 16th to 31st October, the cyclone was actually towards the end of this. All right. And what do you see over here? And so you see cyclone, you see pre-cyclone, cyclone, and post-cyclone signatures over here. Okay. What do you see over here? You see that in fact the order parameter is much smoother, and correspondingly you see a very steep jump in the susceptibility over here. So you see a large discontinuity here. All right. You should actually notice the numbers which are labeling the axis. The right side is actually the labels on the order parameter, that's normalized, so that's from 0 to 1. On the left side, you actually see the susceptibility, and you will see that in the cyclonic period, and so Kyant is, for this is when the cyclone is actually in the system. You can see that the susceptibility jumps, the susceptibilities are actually much higher. Okay, so 0 to 60 over here, and that I think is just 0 to 35. All right. So that jump in the susceptibility is also a signature of the fact that a very extreme climatic phenomena is happening. Okay. I'll just show you the other 2 in this year. Okay. So these were successive cyclones. I mean, we didn't deserve this, okay, to have them one after the other like this, but we did. So the one after that was Cyclone Nada, which came shortly afterwards. It came in November and it passed on the 2nd of December. And here is the finer data. And you can see a similar feature over there. Okay. The thing which you should notice over here is the susceptibilities on the right hand side. And so remember that the cyclone, here also the cyclone is coming on 29th November. So it is coming at the end of the right hand network. And you see how high the susceptibility values are there, 0 to 400. On the left you can see those, as compared to the susceptibility values on the right. Okay, so now here is Varda. Varda was actually unusual for a variety of reasons. Wind velocities there were very high. Okay. As per the Met Office, it lasted very long. So it was a long sustained cyclone. Okay. So 6th to 18th December, that's 12 days. That's much longer than the others. All right. As I told you, it hit Chennai very badly. Okay. Many of my colleagues had to hack their way out of their houses because trees had fallen in front of their doors. So what do you see on the left? You see a network on the left, which is 1st to 15th December, and on the right you see a network which is 16th to 31st December. So here you can see that in fact the active period of Varda was actually over both these networks. All right. So this has a certain consequence. One is that this is fairly discontinuous. This is, you can see that there is a very steep jump in the susceptibility, but there are fewer jumps here than you saw in the other cases. Okay. Here, in fact, the jump is so steep that you, in fact, essentially, I mean, there are still fewer jumps here than there, okay, which is why I wanted to show you this data, which is finer data. And the other thing to notice is that this was a very severe cyclone, okay. Because this is a very serious cyclone, both in that part and in this part, you can see that the chi values are pretty high. All right. So I'm out of time. Bala has been very kind. He has allowed me to take up other people's time. So I'll leave all this, come over to IIT, I'll tell you all this anytime you want. Including a correlation. We can actually see a rough correlation with the cyclone path, which is not so trivial, okay? Here, for example, this is Varda, okay? So what we see over here is the degree, the nodes of high degree, and you can see how the distribution changes from before the cyclone to after the cyclone, or rather these two networks which we saw. And this actually shows you the section of the Indian Ocean which we are actually considering. But let me so what have we seen? So I was highly enthusiastic. I added a lot of things which I do not have the time to present. So what have we seen? I'll just tell you what we already have seen. This is a talk which I gave a while ago. So in fact, the conclusions are up to the point which I presented. So you can see that distinct discontinuities are seen in the order parameter in the cyclone period. After the cyclone, the discontinuities smooth out. Okay. You can see the Kant signatures, the Nada signatures, and the Varda signatures in the appropriate networks. Okay. Since these cyclones were close together, the networks kind of overlap. Okay. So in some cases, the post-cyclone period for one is the pre-cyclone period for the next one. Okay. And you actually see complicated features there. Okay. And each cyclone, I think, has its unique signature, which you see in what are called the micro transitions, which I don't really have the time to tell you about. So let me tell you what the outlook is, and then I'll stop that. Okay. So nodes of high degree and betweenness centrality distributions, they also show the signatures. They can be compared with the path of the cyclone. Okay. So this is work in progress. With high degree, we have already got some results. Okay. The micro transitions show characteristic structure. So each one carries its signature. Okay. You can actually use the micro transitions for predictions. Predictions in the case of at what correlation values will you actually see a large connected cluster, okay? A giant connected clusters. Okay. These are general methods. Okay? So why, they shouldn't only be confined to tropical cyclones. They could apply to hurricanes. They could apply to cyclones in. They should apply to typhoons. None of these methods have been used for these things before. Okay? So that's another problem worth doing. And we've used a 16-day grid. We have used a 16-day network and a grid which is confined to the Indian Ocean. Okay? And we already see something. Okay? If you want to do sensitive predictions, or if you want to analyze sensitive features, you may need to change these. All right. So you need not take these as given from God. Okay. And other geographic locations, they need further study. But I'm perfectly confident that as far as this kind of climatic phenomena is concerned, these methods will work. So with this, I will stop, and thank you very much for your time.
Nilima, I'm just curious, so you did this with the temperature correlation. So suppose you had some other, do you get a similar network, or I'm just curious? Well, it's probably hard work to do it, but I was wondering if there's any other parameter which gives a...
Come, let's do it.
Okay.
Because I believe it will be the same.
Because it's interesting to see if there is some other thing, like almost like you can even have a multiplex, like, here's a network, there's a network of maybe...
I see. I mean, like, look, we are constantly getting these climate refugees, okay? And they have these kinds of
questions. I wasn't there.
No, you're not.
They definitely have wind velocity.
Yeah, and humidity.
Humidity, dew point, I mean, standard that's why I was asking whether it's over land or sea. It's over the sea for uniformity.
Variables, they should have similar.
But you might have a land.
There's some.
So one more small question.
Wind velocity pressure won't matter. Okay, wind velocity might. So it really is a question of what? Because these are climatically, these are very different things. Okay? And finally many climate phenomena, they are related to these large circulating things in the atmosphere. The Rossby waves, the this wave, the that wave, etc., etc. But these are small scale phenomena. Okay? Tropical cyclones are actually small scale phenomena. So they are related to very detailed circulating structures. And we just have to identify them. We don't know. And each one of them might be different. Okay?
Just one small clarification. In the first point here, nodes of high degree, this is for, so this might be a different node in the next network in a different way.
Yes.
Yeah, so it's actually like a temporarily changing network.
So if I showed you the others, I showed you Kyant, I think. I showed you Kyant, and I don't think I showed you Nada. But if you try the other cyclones, you see something. If you want to see, I'll show you one minute.
No, it's okay. But it should be correlated with the spatial event, right? Very strong.
Yeah. So in fact, just see the picture for 1 second. Please excuse me, Bala. So that, see, this is how you plot. So this is okay, which is different from Kyant and Nada. This is the next year. This is cleaner because it was a single cyclone. It didn't have those confusing features which come from overlapping cyclones. Alright? Okay.
Any other questions?
Maybe just one.
Just a comment.
Just as a background benchmark, did you try when there was no cyclone at all to see if you had those transitions? Didn't exist.
Yeah. You see, you take any other thing, you see, I mean, you see that susceptibility jump going, right? So it goes. I mean, you have a peaceful period, you don't see it. I mean, you see jumps due to other features. See, this is the climate. There are 100 things happening all the time. So something shows, okay? So that is why here the geographic scale and the time temporal scale, they are important.
Thank you, Nilima. Before I wind up, let me inject a historical note. The India Meteorological Department is the oldest scientific department of the Government of India, set up in 1863. And the Viceroy at that time was pleased to sanction the grant of 300 observers across the country, who often went on horseback to the Stevenson screens in which the data was accumulating, take the data and transmit it to say, headquarters like Kalipur or Colaba and so on, twice a day by telegraph. And they had for this entire subcontinent just 300 stations, in most inhospitable terrain very often. And the data is available in Pune actually, in the Met departments.
Office, as we call it, because it moved from Shimla. And another historical fact, Bala's father actually worked for the meteorology.
Thank you, Nilima.
Thank you.
Just the thought that minimum qualification for the job is horseback riding. I mean, not just a PhD.
They were paid 10 rupees a month, the observers. The next talk is by Dr. Aradhana Singh of ICER Tirupati. She will speak on navigating the mammalian brain ensemble.
Sorry, to call you help once more.
What is the view you want to select? Mirror arrangement on the display. Oh, okay. Let's go. Okay. Just go back to the presentation.
Can you give this to
I'm sorry? I'll give it to the person.
So, good afternoon, everyone. I'm Aradhana Singh, and actually, I want to mention that my association with Professor Sudeshna is she was my thesis supervisor external. So she had examined she was one of the examiners. She was physically there. So yeah, I'm very thankful to her. She was the coolest examiner I could have. Yeah. So, I will discuss my current work, which is on the mammalian brains, and network has already been introduced by Professor Nilima, so I will skip that. I will just mention that I am studying the brain networks, and the network theory has been really very successful in finding the some understanding about the brains and its functioning. So, the brains are understood at the macroscopic level as well as the microscopic level. So the microscopic level, the nodes in the brain are the neurons, and the connections are the synapses connecting them. And the full mapping for all the species is not possible. Only the C. elegans and the Drosophila has been fully mapped. The C. elegans is having 385 neurons with 4,887 chemical ages, and Drosophila is having 25,000 neurons with 20 million chemical synapses. And if you think about the higher level species, you can imagine that such kind of full mapping is currently not possible. In case of the mammalians, they have billion of neurons. So there the mapping is done on the basis of the different brain regions. So the nodes are the brain regions, and the connections are the projections, that is the density of white matters between the different brain areas. And there also there are two type of networks. One type of network are the structural brain network, where the different methods, like histological or the imagining data has been generated, and then the network is created and is understood. And another type of networks are the functional brain networks, where the recording of the different brain regions has been done using the different techniques like fMRI, MEG and EEG, and the network is constructed and their analysis has been done. So a traditional way to study the brains is to understand what's the role of different nodes in the networks, which is the influence, and influence is determined by the degree participation or the betweenness centralities, and the segregation is studied using the clustering motif and the modularity matrix, and the integration is studied using the distance, path length, and efficiency. So I think everybody knows about all these things, but still I will tell some little bit. The degree is the number of the edges passing through a node, and in this graph we can see that this node is the highest degree node and this node is the lowest degree nodes, and the segregation in clustering, how the neighbors are connected with each other. So you can see that this node is having high degree as well as having very high clustering. And similarly, modularity is also the existence of this dense connections between the group of the nodes in the network. And integration is the how much steps you need to reach from one node to another node, which is the communication distance, the path length, and that also decides the efficiency of the network, that how fast the information can propagate on a network. And the next one is the rich club. The rich club is the high degree nodes tend to be more connected with each other. So I had a good example of that. You can see the people who are sitting on the front seats, they are the rich club nodes. You can see they know each other. They are well connected. So if you will form a collaboration network, you will find that these are the rich club.
No money, no knowledge. You start losing here, you get very here, that's what is meant club. Nothing else about it. Start science actually.
So, as per network theory, the fundamental principles of brain organization is brain needs segregation as well as integration. Segregation is important because brain is the physical network. It needs cost for its functioning. So, in case of this, if you have the connection between the nearby regions, then the cost will be less. So such networks are the regular networks, where the connections are only between the spatially nearby regions. So those networks are most cost efficient, whereas the efficiency is not good. So if you go to another hand, which is a completely random network, you'll see the efficiency is maximum for these networks. But these networks are not cost efficient. So the brains are like optimized in such a way that they have both the low cost as well as high efficiency, and which is the case of the spatial small world networks. So like we had a collaboration with the experimentalist from like Professor Yassiv and Yoshi and Yaniv from the Tel Aviv University, Israel, and they had done this all experimental part and doing the diffusion tensor imagining and getting the data, and we got data from them, and we had the data of 124 distinct mammalian brains, a total of 226 brains, and each brain was divided into 200 cortical segments, 100 from each hemispheres, and we had the link weights. It was a weighted network, and also it had the XYZ coordinates of all the nodes. And the brain sizes of these species varied from 10 to the power minus 1 to 10 to the power 3 milliliter. So like the earlier work has shown that there is an impact of brain size, and the brain volume is directly correlated with the average number of the neurons, like average number of the synapses per neuron, as well as the glucose metabolism. So bigger the brain, more energy is required for its functioning. So we had a natural question being from network science that how the network structure changes as the size is changing, because we have like the networks, brain networks of a fruit bat to a dolphin. So what is the impact of this size on the network organization? So we studied from that point of view, and we started studying first the segregation and integration. So the segregation is like you can calculate segregation by finding the modularity coefficient, which is the metric for the how the network is segregated, and we see that this is the x-axis is the brain volume, log of brain volume. And we see that almost all the brains, like irrespective of this volume, is ranging from the 0.01 to 10 to the power 3, but the modularity coefficient is almost same for all the brains. Similarly, the communication efficiency, except for a few outliers, like the communication efficiency is almost also same. So we could see here that in spite of the different brain sizes, the efficiency as well as the modularity is remaining same. So it's not like that the bigger brains are smarter. Like the smaller one are doing their work efficiently what they need to do. So this quantity clustering, we saw there was a correlation with the brain volume, but since clustering is also associated with the density, so denser is the network, more is the clustering, and we found that density was correlated with the brain volume, and which is already has been shown, like it has been ended.
So just a quick clarification. So you are looking at structural connectivity, right?
Structural connectivity.
Okay. So when you map it onto the Schaefer atlas, which is a 200 cross 200 atlas, so do you do any parsing or filtering, or you keep all edges?
We are keeping all edges. Like we did all type of studies. Like we put threshold also to study if we can see some changes in the networks, like by just putting the threshold. But we didn't find, so we kept everything same. Yeah.
But you are not keeping any weights, right?
No. So like to tell the story, we are not putting any weights because it's not making any difference in the results. Okay. So next we studied the fibril and distribution in the mammalian brains, and like here we can see that for all the brains the fibril and distribution is bimodal. So like the smaller fibers has highest probability of their occurrence, and as the length is increasing, it's decreasing, but like this thing like the another peak that we are getting for the higher fibers, it is different from that we have already known from the theory, like because theory says that the brain networks have the spatial small world feature, which is given by the power, like the exponential decay of the fibers with the distance, or the power law decay with the distance. So it shouldn't have increased after this point. So So the same behavior we saw at the different scales as well. Like if we divide the brain into 2 parts and see the fiber length distribution, we see in 4 parts, like we divided brain into 4 parts, and we saw that there is a fiber length distribution, the bimodality in the fiber length distribution in this at this scale as well. And like if we keep dividing into different subsections, we found that the bimodality is preserved, like up to 32 parts. Like below that, the number of nodes in each segment doesn't remain significant, so we cannot do the partition below that. So this shows that that the bimodality in this fiber length distribution is scale invariance, and at each scale it is having this bimodality in the fiber length distribution. So it's the bimodality is not just like the global feature, but it's the basic property. Like at each scale, the brain networks are having this property. So if we, like as I mentioned, if we compare that with the theory, like this blue curve is for the corresponding in the model networks, and the black curve is for the empirical networks, and the red dots are for the corresponding random networks. So we can see that the brain networks are up to this, when it's decreasing, it's following this trend, but it's again increasing, whereas in the model says that it should only decrease. And as per the random, it should have the uniform distribution of fiber lengths. So we wanted to look for a reason for existence of that peak, another peak, and so we divided into the data, and we found that what could be the origin of the long fibers, and one of that was that these long fibers were connecting to the distinct modules. Like we can see in this figure, this color bar is showing this fiber lengths, and most of the long fiber lengths are outside the modules, which is the same for this network as well. And for other brains also, we found that the longer fibers are connecting to different modules. And for the ensemble average, we studied the average of the fiber length within the modules and between the modules, and we can see that the 2 peaks are clearly distinct, and the one which is between the modules is having the larger fibers. And also these longer fibers are coming from different hemispheres. So like as I mentioned, rich club thing, we tried to see like whether all these networks are also having the rich club organization, because in some of the earlier papers it has been shown that the brain networks are having the rich club organization, which is the like high degree nodes tend to have denser connections as compared to the low degree nodes. And if we calculate the rich club coefficient, you see that the high degree nodes are having the higher rich club coefficient as compared to the low degree nodes. So there is a rich club organization in the brain networks, but we, in addition to that, we found that these rich club nodes are not only densely connected, but are connected through very long fibers. So you can see that this color bar is showing the length of the fibers, and the high degree nodes are highly connected as well as connected to the long fibers. So the role of these long fibers is to connect the rich club. So this is also another metric, like which is showing the existence of the long fibers are connecting to the different distant brain areas, which are highly connected and also are like most dominant. So next, like so far studies have considered like the degree centrality in order to understand the network, whereas these networks are the spatial networks. So we thought that the length of the connections should also matter when you are understanding the brain. So we came up with new metric, which is the fiber length centrality, which is the average fiber passing through the node. And we calculated that fiber length centrality and studied that there is a correlation between the fiber length centrality and degree centrality, but some of the high fiber length centrality nodes could be the high degree nodes, but the vice versa is not true. So the fiber length centrality is a different metric, and on the basis of that when we divided the network, we found that we can really divide a network, brain network, into two parts on the basis of their fiber length centrality. One part is having the non-localized connection, and another part is having the localized connections. So if we see the fiber length distribution of non-localized part, we see it's a uniform distribution. Whereas when we see for the fiber length distribution for the localized part, we see it's having this exponential decay kind of, which is the characteristic of the spatial small world network. So the brain networks, instead of being just the small world or random, they are mixture of both. Like they are mixture of random network as well as a spatial small world network. So yes, with that actually I will summarize my results, that all the brains exhibit the bimodal distribution of the fiber length, and the occurrence of these long fibers is more than expected from the small world organization. The long fibers contribute to the connecting different modules as well as to high degree nodes, which form the backbone of the network. And all these networks can be divided into two sub-networks having localized and delocalized connectivity profiles. So like we can summarize that in spite of potential diversity in scale and function across the different species, the structural organization remains same. So the story goes to that. That's all. Thanks.
Comments or questions? Yeah, please.
Do you have the data or?
Yeah, we have the data.
Oh, so you don't use the Euclidean
No,
distance?
we don't use the Euclidean distance.
And in the last graph, when you showed
Because Euclidean distance, like in case of the brains, the Euclidean distance could be less important, because in brain, like it's not like from one hemisphere or even within the hemisphere, it cannot be a straight line distance between the two nodes, like because this is space constraint and there is a curvature.
Okay, just one more thing. When you showed the localizing and non-localizing distribution, by localizing you means like the proximity in terms of where the neurons are.
Non-localized means there are more connections between nearby regions as compared to the distant regions.
So what that
So
graph?
they are localized.
Okay, so what
And non-localized are not having any preference; they are having random connections.
I'm sorry, can you explain that?
So
again?
like localized means, like you can understand in terms of the social networks, that when there is no teacher in the network, this class is localized, the friends sit with themselves like.
Okay.
And but when teacher is there, everyone is uniform, like kind of. So having.
How can,
in spatial you could think of different example also, like.
how should I interpret the data in terms of structure? The two graphs, the one uniform distribution and the decay.
How can you? Okay, so this is one network, one brain network, and you can divide this brain network into two parts. So that the one part is having the localized connection, another part is having the one part is having non-localized connection, another part is having the localized connection. So you find that this part is having the uniform distribution of the fiber length, this part is having this small world feature. So instead of
when you say uniform, it means connections between the non-localized.
There is no biasness, like each fiber length is equally probable.
As in the connections within the non-localized network.
Within the non-localized, yeah.
Oh, okay.
See, the brain has a functional organization as well as a structural organization.
Yeah.
So are these correlated? I mean, do you have any idea if the functional organization is correlated with your results in any way?
Actually, because no, for this we don't have, because this is the very large data set, and like the sizes of the brains are so like there is so much diversity in the types of the mammalians itself. So for all the EEG and the data is not available, so we cannot compare. But we can study the dynamics on it, which is the extension of this part which is going on. Yeah.
Aradhana, nice talk. Quick question. So, what is the data set that you got from Tel Aviv, right? So it has the structural connectivity taken for humans and other organisms as well.
Yeah.
Okay, that is why you didn't go to Human Connectome project.
No. Yeah, so that's why we didn't go to, because they have for fruit, fruit bat, they have for horse, they have for donkey, all the almost all type of mammalians. So
will your results hold if you analyze the slew of data if you did a Human Connectome project?
Then we also had that doubt, so we went to our another collaborator, which is Professor Olaf Spons, and from him we got the data for the human brain. So this was the data from different lab, different collaborators, and there also we found the same results. So that's how we concluded that it's not just about the data, it's a property of the brain networks. Because so far, the Faber-Solin length centrality distribution hasn't been studied. Euclidean distance distribution has been studied, because the data was not available. So whatever theory is there is based on the Euclidean distance, not the Faber-Solin distance.
I have a naive question about this.
Yeah, I'm also naive.
Between neurons, there can be more. Between two given neurons, there's more than one connection possible.
Yeah.
So when you say this network analysis is done,
but actually, this is not for the. This is not the network between the neurons. This is between the different brain regions, because.
Connected by what?
Connected by this white matter, which is the. These are the synapses only, but the group of synapses,
I see.
Not the single synapse, the group of synapses.
Okay. Any other questions? If not, let's thank the speaker again. We go to the last talk of the session by Professor Puneet Paramananda. He is going to speak on emergent dynamics for active rotators.
I'll just check. Sorry. This is working. Thank you. Can you guys hear me at the back? They need it for the recording. Oh, I'm a Delhi boy, I can shout.
I know. It's not you can't shout it over the internet.
All right. So I'll put it over here, but then I'll have to moderate. Yeah. Right down to be, right? Is it? This is. Yeah. Okay. Okay. Everybody has been saying wonderful things about Sudeshna, but we should not forget Sitabra. Sitabra, he had not made the effort. I was pleasantly surprised. He just, wrote an email one day and he says, we are planning something for Sudeshna, and so thank you, Sitabra, for this opportunity. Do you have a pointer? And of course, Sudeshna, you guys have had traditions, as the young lady before was saying, rich club. I joined the club very late because I was outside. I was outside the continent for a long time, and she will correct me. She has better memory, Sudeshna. I met her in 2004 in Potsdam for a conference where I was organizing a symposium, and she joined in. And then things happened. SDIC. I landed up looking for a job in India, and I have to accept Ram's help was amazing. And then I just randomly went to Sudeshna, visited this place, and she was asking me what I was doing, so I told her about some numerical work, boring numerical work we had done with chiral systems, and she says, we can do logic gates in this. And within 48 hours, she did everything, and we had a paper. So every time I meet Sudeshna, I get a paper. So it is It's just uncanny, you know. And then again, she has this intuition which is amazing. And I was she was visiting IIT Bombay for a month, if I'm not mistaken. And I was studying with my graduate student about, she was trying to work in echo in brain and stuff like that. And Sudeshna was in the office next door, so when in doubt, go to Sudeshna. Went there, and within a month, sure enough, we had a paper. So by induction, I can safely say up until now, every time I meet Sudeshna for a period of more than 3 days, without interruption from other oscillators, I get a paper. So this is going to be a total paradigm shift. I know you guys are all theoretical and you like mathematical stuff, but this is going to be purely experimental. And it's intentional because the actual work does include numerics, but as this is like an ode to the theoretician that I know and who always helps me if I have any doubts. So I'm going to talk about some collective emergent dynamics in rotators. Rest of the people you can safely ignore. The people who did all the work are essentially the previous graduate students in the group. Ishant now, he started the system. And is very good in numerics as well. He is now at Georgia Tech, and Jyoti has also graduated and has gone to Italy. This work that I'm going to talk about was actually, the motivation was given by Avadhesh in a conference that Ram organized in circa 2008, 9, 10 in Bangalore. And he had this paper about rotators. And people who know Avdesh, he has this inimitable style. He comes up to you and he says, Puneet ji, iska experiments karna chahiye. And it took me 10 years, but we finally got to it. So he has to be properly acknowledged as well. So what am I talking about? We do simple third world country tabletop experiments in trying to give proof of principle. So the thing I work with is, most of you perhaps have seen in some ceremonies over the years, is called Kapoor, the camphor. And the beauty of this thing is that when you put it on a surface of water, deionized preferably, so there's no contamination, it moves by itself. Okay, it can do translation motion. This is the rotational motion. It looks nicer in UV. So what we have done is, I don't know whether you've seen these hole punchers. So you take an A4 paper, get the circle out, dip it in ethanol and camphor, and then leave it on the surface of water. It does its whole thing. Okay. So this is fluorescence, but this is not a new art system. It was studied way back in the 19th century. And the mechanism, which I shall show you in a couple of slides, which you perhaps already know, was provided by this Belgian scientist over there. So we started working, when Ishant started, we said, let's do this system. And he started working with stuff like this, and he also studied some ensemble dynamics, in which you had a bunch of these oscillators and they showed breathing motion, Mexican wave type of motion, all sort of stuff, which I'm not going to talk about. But there was always in the back of my mind, I always wanted to prove what Avdesh had seen numerically. So Jyoti, when she came in, we said, okay, we know this paper shows translation motion, rotational motion. So if we pivot it, can we make rotators out of it? So that's what was the goal, and we started with it. So this is, I'm sorry, I'm supposed to be the experimentalist here, right? So, first of all, oh, I thought I broke something. No, that's okay. I mean, I'm okay with this, right? It's up to you. Yeah, Ram might be scared, but I mean, that's fine. So why does it work? How many of you know heard of the Marangoni effect, Marangoni forces? Tears of wine, legs of whiskey, you do because you worked in the lab with us, Manoj. So essentially, it's a very simple thing that, yes, and it's essentially that, you know, when you have a paper, just humor for a moment, there's a particle, there's a paper which is dipped in camphor. It's a completely circular paper. In numerics, it's easy to do, right? You just make it completely circular. In real life, it does not. So what it does is the camphor diffuses to the solution. But in utopia, and camphor reduces instantaneous the surface, this tension of the liquid interface it's coming in contact with. So it's essentially an interfacial effect, right? Nonetheless, in reality, you cannot have homogeneous diffusion of camphor all around it. The moment that happens, there's an asymmetry involved. So, for example, in this cartoon, you see there are more of camphor here than less of camphor here, right? So there's a lower surface tension here, there's a higher surface tension here. It immediately gets a kick, asymmetric force. And what happens is, when it's moving, it encounters fresh water, even higher surface tension. Consequently, you get an acceleration. And it keeps on going, if you have an infinite channel, till the camphor equilibrates, or it will come to a wall, and then depending on whether the wall is hydrophilic or hydrophobic, the solution, it will have various dynamics. So we were able to study this completely first in the translation, but to do the rotation, we have to do something different. And you will see the results of the rotators are not in fluorescent because we needed to monitor the tip to get the x and the y coordinates. So they look ugly, but the results are valid. So what we did was, we again took an A4 paper using MS Paint. We made it black. Then we printed it out, and we put a white dot on it using MS Paint as well, so we can track its coordinates to the best of our ability. Then we dip it in the camphor ethanol solution, alcohol evaporates, and what you have is a camphor laden paper. And then you pivot it. You want to study synchronization. I'm not going to even explain it to you. Ram did that for me in the morning. And you see what actually happens. So this is the dynamics of a single rotator. Okay? So you see, as you could probably imagine, as time goes on, the system equilibrates, starts getting smaller, slower and slower, and eventually, at this long enough time, everything equilibrates and system stops. 6-point dynamics, right? So we are working in the domain of transients, but we decided to work in this interval so that we could at least get 400 cycles of rotation to do our experiments without drift velocity being that much. If you put it up there, immediately you lose velocity and the system gets all confused about it. But to study synchronization, we made 2 such pivots, put them in a nice, I wouldn't say jar, what would you call it, basin or something like that, and just watch the evolution in real time. And I mean, I hate to say that, but you don't even need to do an analysis. If it synchronizes, you will see it is synchronizing, okay? So what we do first is, well, what Jyoti did was she had 2 these rotators, and the initial direction could be clockwise or counterclockwise, stochastically chosen. But the important point I would like to emphasize and perhaps reiterate later is that once it chooses a direction, it ain't going to flip the direction. So if it goes counterclockwise, it shall stay counterclockwise. If it goes clockwise, it will stay clockwise. So in this case, the white pots were used for tracking and getting the coordinates. You see each one does it all, its own stuff. So if you plot the Lissajous figures of the 2 x and the y pixel values and the y1 and the y2 pixel values, you see, as Ram showed you, absolute 0 correlation between the dynamics of the 2 rotators, okay? So now we systematically brought them together. Means, since the coupling is through the camphor, the coupling coefficient is inversely proportional to the Euclidean distance between the 2 rotators. All right? So you have these 2 domains that we see, in which on your left they are co-rotating, and on your right they are counter-rotating. and the distances between them is less than 2L. So I don't really need to do any analysis. They are synchronized. In some phase locking is happening. Otherwise, if they are not synchronized, they will touch each other. And this keeps on going for 400, 500 cycles, and in real time is just 8 minutes, but I mean that's not, it goes on. And what we realized after doing it numerous times, that this seems to be more probable. I'm not going to give you a statistical number, because we didn't do any statistics, but it seemed to be happening more and more. And then we started thinking, why would that be? But it turns out, in hindsight, this is why it happens. So if you look at the co-rotating domain vis-a-vis the counter-rotating domain, in the intersection area, in the area of influence of the camphor layer through which the interaction takes place, for the second domain, they go in the same direction. So although if you start co-rotating, if you get into that domain, you ain't going to switch back. As I said, momentum supersedes coupling. Nonetheless, it is more favorable because you move from lower surface tension to higher surface tension because of the Marangoni force. Same in this case. In this case, there should be, in the intersection area, there is symmetry of the flow in the system. In contrast, here you have to make an effort. So it kind of makes sense that the counter-rotating domains are more preferable. For the last time, it does not mean the co-rotating don't happen. It just don't happen. When they happen, they stay. It does not happen that often. Okay? When you have to publish, you have to do some analysis also, although it was visually. So, and this was another thing which Avdesh kind of predicted in his modeling. So you looked at, for the co-rotating domains, they were kind of, synchronized with the two attractors. These are experiments, so you're not going to see a single line on the 45 degrees. You have a sort of a lag synchrony, and they show 45 degree. But what is interesting is, for the counter-rotating, they seem to be, in the simulations which we did, we saw 135 degrees. It kind of, if you're charitable to me, you can convince yourself they seem to be out of phase with a little bit of delay. But if you're not, I'm not going to insist. But it's definitely not 90 degree. So this is what Avdesh called was some sort of mixed synchrony. So for one domain, you have a certain type of synchrony. For the other domain, you have certain, just counter-rotating and co-rotating. But I shall insist that these are very robust results. This happen all the time. They were so robust that we ventured into doing something more expansive with them. So these are with two oscillators. Then we said, let's take a journey when we have multiple oscillators. What is going to happen? So in this case, I need to clarify the nomenclature. It does not matter whether I'm counterclockwise or clockwise. If both of them are counterclockwise, I call it a co-rotating bond. If both of them are clockwise, I call it a co-rotating bond. Any other scenario, I call it a co-rotating bond. So the individual sense of rotation is relevant. It's the pair which counts, okay? So we started doing with different configurations. This is the journey through the visual aesthetics, I think. So here you see 3 ribbons on a line. You can see the B1 here, this and this, out of one is co, one is counter, and the same here. You have different, but I'm just going to show you. There are sisters configurations also. There are lots and lots. So this is a counter-rotating bond, this is a counter-rotating bond, and this is shown here. These are different bonds we'll see. Again, no statistics, we just wanted to see what sort of different configurations we see. Then we placed 4 on a line. This is by no means the exhaustive list. So here I'm showing you the C1, in which you see the first one is co-rotating and the other 2 ones are counter-rotating bonds. Okay, other bonds are also possible, which we saw. Again, no statistics done, but visually we could confirm a lot of different configurations, synchronization domains configurations that we could notify. Then we wanted to see frustration, so we said we'll put it in a triangle. We never got to saw it. We never got to see it. So this is the configurations we did see. This is the simplest one, in which all of them are co-rotating. This we could not see. There were couples we could see, the couples, there's a couple of them we could not see. I think this is due to geometrical constraints, and I mean, we wanted to see frustration, but we could not see that either. Then we put 4 ribbons on a line. I'm going to show you 2 representative configurations. So this corresponds to B. You can convince yourself you have 2 co-rotating bonds and 2 counter-rotating bonds, and this one corresponds to C, in which you have all counter-rotating bonds. Okay? More and more. I think this is the last one. We had to do star because I think Sureshna was there at that time and we were struggling with it. And of course, she had one point star bhi karo, so we did star as well. And we saw different configurations, and the one I'm going to show you is B, in which you have, I think it's B, right? Yeah. So I have 3 co-rotating bonds and 1 counter-rotating bond. Yet, to emphasize, and for the last time, there were other modes, but I'm just showing you one which kind of shows you what different configurations you have, and this is what we did. Okay.
Why is there no drift of the pivot in any of these cases?
Because they're clamped, sir. Yeah, there's a glue. I think it's otherwise there's no point, right? How much time do I have? 2 minutes. Oh, no, okay, quick. I shouldn't have asked you, right? Of course, and this I clearly remember. I'm sorry.
I didn't say anything.
No, yeah. So I remember this. I clearly remember we were struggling, Sureshna, when you were there. Everybody has to do Chimera in India. And it is so overrated. I'm sorry, I should not say that. We used to call it in our good old times partially synchronized states. I think Sureshna has also worked on it with coupled map lattices, a lot of people. But we had to do it. This was the final chapter of Jyoti's thesis. So I said, so what we did was, it ain't going to work when you have distance between the 2 pivots less than 2L. Because the moment you have the unsynchronized domain, it will hit each other and you'll stop. So what we did was, we made the distance a little bit. The simpleton logic for an experimentalist was, you have synchrony when the Euclidean distance is less than something. You have total asynchrony when the Euclidean distance is greater than something. In between, perhaps we can see something which is a mixture of synchrony and asynchrony, which is essentially chimera. We call it chimera-like because the oscillators, regardless of how much you try, they cannot be identical, right? So we call it chimera-like states. And we, just to make sure, we put the concentration a little bit wrong. So these are more than 2L, and I think you should be able to convince yourself that all the 1 and 2 are synchronized, 1 and 3 and 2 or 3 are not synchronized. Because I can't say, they'll touch because the distance is greater than 2L. So essentially we plotted the tractor plot with the variables, and you see lack of correlation, a healthy correlation, cross correlation between the 2 oscillators. Okay? All these work has numerics if you're interested, but I didn't want to show that. And the last thing we did, coming from chaos, we wanted to find chaos. We wanted to find aperiodicity. Is there a hand at the back?
I just want to ask, you tried this at different temperatures or?
No. Bombay temperature always hot. Yeah. Oh no, sorry, I'm sorry. Actually AC on, right? So it was done at, I should say 24 degrees centigrade. Or 23. I don't know how the kids do it. I do it at 24. But no, we did not. No.
Do you expect any different kind of?
They'll go perhaps the dissolution, the dissociation of camphor will be faster. But I don't know vis-a-vis how it will affect the coupling. I would be tricking you if I say I did. All I know is the Marangoni effect is not Thurbin-Marangoni effect here. This is the solute Marangoni effect. So it's due to the surface tension difference is due to difference of concentration of the chemical regarding that. Because you know surface tension, maybe that's where your question was. The surface tension also changes with temperature. We did not study that. Okay. So finally, we made the contact area less, the exposed interfacial area less, and after 3-4 months of tinkering with it, we were able to find a stop and go, and you'll see it also flips signs when it goes. So you have to imagine this is the pivot. So I know it's a bad quality. Because, see, we couldn't do fluorescence like the other thing because we had to monitor the white dot. So and then you can do this thing. So when we did the experiment, after that we did entrainment also. I didn't want to show you that. So you'll see that now it will perhaps go the other way. So we were able to find aperiodic bursting using camphor also. So it turned out to be a very simple, fruitful system in which it's very cheap, camphor, deionized water, A4 paper, that's it. And we were able to study that. But still we are working on it. Of course, the histogram shows, this is the last 2 slides. So this is now this is Ishan's work actually. So we started making filaments out of this because Ishan Raghu, our collaborator, wanted to work with flagella-like movement on a millimeter scale. So we have 18 such discs connected by a fishing string, and you can see the different, this is work in progress, although Ishanta has left, so I don't know what will be the asymptotic solution of this paper. So we can see it's like by changing the distance between the 2 pivot points, either you see in phase, see these are the monitoring of the space of these last 2. Out of phase, this is still work in progress. And finally, we saw something which all of you guys perhaps know is a relay synchronization. So this and this in phase, and the middle one out of phase.
This is also pivoted at one.
Yes, but the only thing is it's not a single thing. It's a collection of 18 such. What is it called? Discs. Not even discs, circular paper, 2-dimensional paper, and connect.
Where is your pivot? At the bottom.
I mean, that's the only thing we changed. Oh, I'm sorry, that's not moving. So, yeah. Okay, I'm done, sir. Yeah, with that, I thank you for your patience. Oh, yes, but there's a moral to the story. Provided you've understood this, in the evening I'm going to ask you, is there going to be wine?
You have to pay for it.
Yeah, but there will be. So, can you, using what we all learned in the last 20-25 minutes, tell me whether a quality of wine is good by evaluating the strength of the tears or the legs of the whiskey, whatever. So think about it. There's going to be a quiz about that. Okay. And with that, I thank you for your attention. I'll take any questions. Oh yes, but then you get targeted motion. If we could, if you make a crescent, you see there will be a geometrical inhomogeneity of the camphor. So you'll have targeted motion. We didn't want that. See, if I could draw here. See, in this, the initial is there a chalk? Okay. There was a reason for this. If you have, okay, my circle is equally bad, but imagine you're assuming that, the diffusion would take place equally. It's only this infinitesimal stochastic fluctuation or some inhomogeneity in the paper you made that will give you a lift. But if you have something like this to start with, you can have, people have done that. People have studied targeted motion, but we didn't want targeted motion regardless, but you can make it go various ways. People, a lot of Japanese collaborators have worked with the camphor boats. We use paper because paper is cheaper. They actually have boats, and they can make them, navigate them to various labyrinths and stuff like that. Any other question? Yes, sir.
Can you show me that you have done that rotator experiment with the strip of the paper?
Strip. Wait a second, I'm going back. This one?
No, the previous one. Yeah.
Which one?
Yeah. So now you are having a strip and it is pivoted at one end, and another end you are having the camphor. That
Camphor is not there. Camphor is on the paper and it diffuses.
So
I want to make that clear.
Yeah. What is the circle?
Sorry? That's the pivot.
No, white circle.
That's I told the white dot. How do we?
Okay.
You saw no, yeah, because that's very important. Otherwise, how do you publish? See all this.
Yeah, I understand. So now the question is that what will happen if you pivot that one at the center of the paper or center of the mass of the object?
We tried that.
So automatically
it was like a flip flop. Yeah.
Okay. And so now the question is that how you can effectively control the coupling between the rotators?
We did it by Euclidean distance. Also, you can make it weaker by using less camphor. These are two tangible things you can change which are in your hand. But there is no scaling. I can't tell you the coupling strength as a function of the distance. I mean, it will be still possible. Yeah, exactly. The scaling, I mean, we don't know. And definitely not as a function of the concentration.
Okay.
All we know, it does change. That's it.
And also viscosity of your medium also. Please.
We are using water. We're not even going there. Hi, come on. No. Deionized water, simple. Even a chemist will not hesitate giving you deionized water. Yeah.
Hi. So while doing the simulation for this, apart from Marangoni effect, what are the other forces did you take?
We did not even use, we just used repulsive coupling, Yukawa type potential.
Okay.
It was a toy model, and if you bother me too much, I'll ask Ishant to write to you, because we did the experiments. The modeling was not, we did not do any hydrodynamics, we did not solve any Navier-Stokes, we just used Yukawa potential, assuming there's a repulsive coupling.
Okay. So you did not take into account any stochastic nature
and
of...
to reiterate, we did not.
Okay, yeah. Thanks.
So there was also, I wanted to ask you.
Yes.
There was no hydrodynamic impact.
Nothing. I mean, we did not take into the numerics.
Numerically, I mean, in reality, with this camphor system, the surface tension differential is a much greater force than
hydrodynamics. I mean, hydrodynamics could play a role, I would imagine, because we tried some experiments where we could not get synchronization, but then we put a magnetic stirrer at the bottom, and then it was able to work. But that sounded too much artificial, because there also how much you rotate by, there is no linear augmentation of coupling as the rotation. And then we wanted to avoid vortices. Yeah. Because if you make it very, then the bubbles start forming, and then that's cheating. Mm-hmm. We didn't want to cheat. Mm-hmm.
Why Yukawa potential?
Sorry?
Why Yukawa potential explicitly?
It was simplest potential.
You could also take the 1 by r.
Of course. Just because my cat is grey doesn't mean your cat has to be grey.
Yukawa is complicated than 1 by r.
We used Yukawa because we had a Yukawa code. Total honesty you'll get from me. Yeah. Why invent something new when you have something in house? Anything else?
So you think you got any insights into why Huygens clocks were anti-sync and all
Yeah, this is what we were thinking, huh? So we actually had this. I don't know whether you were there for Jyoti's exam also. We discussed that. I mean, this is something to do by in Huygens also you get absolutely. So but then that's I think a very pertinent question, which lower energy is
higher energy.
Yeah, but But that's what, since he was...
Yeah, see, this is, maybe the air, again, I'm not, because, not in front of a guy who wrote a book on classical mechanics, but, no, but it's a good question, because what do we see? When you have anti-sync, when you have repulsive coupling, isn't that correct, Rishna? Because x1 is equal to minus x2. That's the solution of the coupling term. But it's not that trivial. Maybe Ram has some insight. No.
You see this child's toy with a whole lot of rotors?
Yes.
Anti-ferromagnetic.
Yeah.
Opposites, what you call counter-rotating.
Yeah.
That's the easier mode to generate.
No, but the thing is why? Why? And in our thing, I think we are fairly convinced we are right. Because in the intersection area, it's a little weird, right? One rotor going from high to low to high, and the other one, the direction has to change. But as I insisted, and once momentum supersedes coupling, once you go in a certain direction, the torque or the momentum will keep on going. Then in our hours of looking at the videos, we never saw a flip, except when we did the aperiodic one. Due to coupling, we never saw a flip. And we still don't know. I think that's I think we discussed that with you. Okay.
Just one. Did you see a lag lead phenomenon? You obviously do, right?
Yeah. Lag. Yeah. Well, the kid has gone. Now they don't even, they ghost you on the emails also. We have been trying to finish that thing and nobody asked. I mean, they have to go to a new place, they have to set the, So yeah, there's a lot to be done, but the problem with working my style is when the kid goes, we stop that system. So now we have to look for something else. Yeah, if it is good enough, for example, with this we got 2, but I mean, there is only so much you can beat the old dog, right? I mean, so and it's no more fun. After a while, it gets boring. When you can predict everything, then it becomes boring. Yeah.
Thank you, Pari.
Yeah, thanks.
Let's thank all the speakers of the session.
Thank you, Professor Balakrishnan. So we'll now break for lunch. Lunch has been arranged in the cafeteria on the first floor. So essentially, please follow the crowd, and you have to go up the stairs to the floor above where lunch has been arranged. And please be back here within an hour. That is, we start the next session at 2:15, 2:15.